away, but could still receive enough energy to support life. The presence of two suns could also offer certain advantages, such as a more stable climate over long periods of time, as the stars' gravitational interactions could help keep the planet's orbit in a stable, predictable path. The atmosphere of a planet in a binary star system would play a crucial role in determining its habitability. With two stars emitting varying levels of radiation, the planet's atmosphere would need to be thick enough to shield the surface from harmful ultraviolet and X-rays, particularly if one or both stars are more active than our Sun. At the same time, the atmosphere would need to allow enough light and warmth to reach the surface to support life. On a binary planet, the interaction of two stars could create stunning atmospheric effects, perhaps vibrant auroras caused by the magnetic fields of the two stars, or clouds that glow in the light of both suns. The mysteries yet to unfold. As we continue to discover more about binary star systems and their planets, the potential for life in these worlds remains one of the most tantalizing questions in astronomy. With missions like the James Webb Space Telescope and upcoming observatories designed to study exoplanets in detail, we are on the cusp of a new era of exploration. These powerful instruments will allow us to probe the atmospheres of circumlunar planets, searching for signs of water vapor, oxygen, and other biosignatures that could hint at the presence of life. Binary star systems, with their dual suns and complex gravitational dynamics, are just one of the many types of planetary systems that challenge our understanding of the universe. They remind us that the cosmos is far more diverse and surprising than we ever imagined, with environments that push the boundaries of what we think is possible. And as we gaze through our telescopes, looking for new worlds, it's entirely possible that the next great discovery in the search for life beyond Earth could come from a planet orbiting two suns, a world where two stars light the sky, and where the story of life is being written in the glow of their combined brilliance. Water-rich planets, oceans beyond Earth. Water, the foundation of life as we know it, is not unique to Earth. In the vastness of the cosmos, scientists believe there are entire planets where water is not just present, but abundant. These water-rich planets, sometimes referred to as ocean worlds, represent some of the most intriguing destinations in the search for life beyond our solar system. Imagine worlds where oceans stretch unbroken from horizon to horizon, where the land, if it exists at all, is submerged beneath kilometers of liquid water. These alien oceans, while familiar in substance, could hold secrets and surprises far beyond our understanding. The science of water worlds. Water-rich planets are believed to have formed in the colder, outer regions of their planetary systems, where water ice was plentiful during the formation of the planet. These worlds may have migrated closer to their stars over time, bringing their vast reservoirs of water with them. Unlike Earth, where water covers roughly 70% of the surface but remains relatively shallow in comparison to the planet's overall size, water-rich planets may be dominated entirely by deep oceans. Oceans that could be hundreds, even thousands of kilometers deep. In these worlds, water would likely be a fundamental part of the planet's structure, creating unique layers of ice and liquid depending on the temperature and pressure. Beneath the vast surface oceans, immense pressures at deeper levels would force water into different forms, such as high-pressure ice, which is not the frozen water we know, but a denser, more solid form of ice that can exist even at high temperatures. This layering effect could create entirely alien ocean ecosystems, where life might thrive in environments more extreme than anything found on Earth. Some water-rich planets may even contain an ice mantle, a layer of ice beneath the liquid water, formed by the immense pressure of the overlying ocean. Such a planet could still have active geological processes below this ice mantle, similar to Earth's mantle and core. In these cases, hydrothermal activity could occur where the planet's internal heat causes cracks in the ice, releasing heat and chemicals into the deep oceans above. Such environments would be similar to Earth's deep-sea hydrothermal vents, where life thrives despite the absence of sunlight. Oceans that cover the world. Imagine standing on the surface of one of these planets, if you could. The view would be unlike anything you've ever seen. An endless expanse of water stretching out in every direction, with no land in sight. The atmosphere might be thick with moisture, constantly feeding the ocean below with rains or creating immense clouds that hover above, reflecting the light of a distant star. The color of the water could vary depending on the planet's chemistry and the light of its sun, from deep blues to greens or even darker hues, colored by unknown elements or biological life lurking beneath. These water worlds could have unique weather systems, driven by the interaction between the ocean and atmosphere. Without land to break up weather patterns, massive storms could form, with winds and waves far more intense than anything we've seen on Earth. On some water-rich planets, superstorms could last for centuries, driven by constant heat exchange between the ocean and atmosphere, creating monstrous waves and towering clouds that spiral across the surface. The deeper oceans would likely be completely alien environments. On Earth, our deepest oceanic trenches extend about 11 kilometers below the surface. But on water-rich planets, these depths could be multiplied many times over. At such depths, life on the surface would be entirely absent, creating a dark, pressurized world where exotic forms of life could evolve. Chemosynthesis, a process where life forms derive energy from chemicals rather than sunlight, could be widespread, just as it is Earth's deep sea. The creatures on these planets that exist might be adapted to live in complete weakness and under incredible pressure. They could be unlike anything we've ever encountered. Large, slow-moving organisms that glide through the deep waters, or entire ecosystems based on floating mats of microbial life drifting just below the surface. The possibilities for life on such planets are vast, and as yet unexplored. The atmospheres of water-rich planets. The atmosphere of a water-rich planet would be an essential factor in determining its habitability. In many cases, water worlds may have dense, thick atmospheres rich in water vapor, creating a greenhouse effect that keeps the surface warm and stable, even if the planet is far from a star. The James Webb Space Telescope and a future mission will allow us to study these atmospheres in detail, searching signals of water vapor, clouds, and gases that can indicate the presence of oceans and potentially life. On some water-rich planets, the atmosphere could be in. The vast surface oceans could contribute to rapid evaporation, creating an atmosphere heavy with moisture. This moisture could condense into massive cloud systems that circle the planet, creating endless rainstorms and contributing to the planet's dynamic weather. In some cases, these atmospheres could be so thick with water vapor that they create a steam world, where the surface is a boiling ocean of water vapor and liquid, surrounded by towering clouds. In more temperate water-rich planets, the atmosphere might resemble Earth's, with a balance of nitrogen, oxygen, and water vapor, possibly giving rise to clouds, rain, and even snow. However, the lack of land to anchor weather systems could mean that the entire planet is subject to frequent and powerful storms, with winds and waves far stronger than anything seen on Earth. In terms of habitability, the presence of liquid water is a key factor, but the atmosphere also needs to protect the surface from harmful radiation and provide a stable environment for life to thrive. Water-rich planets orbiting M-dwarf stars, which are known for their intense flares of radiation, need a thick, protective atmosphere to shield the oceans from these bursts of energy. In some cases, the thick atmosphere of a water world could help regulate temperatures and protect against such radiation, allowing life to evolve in the oceans below. Europa, Enceladus, and the ice moons, clues from our own solar system. Exoplanets with oceans are tantalizing prospects. We don't have to look far from home to find examples of potential water-rich worlds. Some of the most candidates for oceans beyond Earth lie within our own solar system, on moons like Europa and Enceladus. Europa, one of Jupiter's largest moons, is covered in a thick shell of ice. Beneath that icy crust, scientists believe there is a global ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. The Europa Clipper mission, set to launch later this decade, aims to investigate Europa's subsurface ocean, searching for clues about its composition and whether it might harbor life. If Europa's oceans contain hydrothermal vents or other sources of chemical energy, it could be a prime location for extraterrestrial life, living in the dark, cold waters beneath the ice. Similarly, Enceladus, a small moon of Saturn, has captivated scientists since the discovery of water ice plumes shooting from its south pole. These plumes, which contain organic compounds, are thought to originate from a subsurface ocean beneath the moon's icy crust. The heat required to keep this ocean from freezing likely comes from geological activity, similar to what we see in Earth's oceans near hydrothermal vents. These plumes have been sampled by the Cassini spacecraft, and the findings suggest that Enceladus could be another potential home for life. While these moons are much smaller than the exoplanets we imagine, they offer critical clues about how water-rich worlds might form and behave. Studying Europa, Enceladus, and other ocean moons gives us a blueprint for understanding how deep oceans can exist in environments far from the warmth of the sun and how life might thrive in such extreme conditions. Super-Earths and subneptunes, likely water-rich planets. Many of the exoplanets discovered by the Kepler Space Telescope and other missions fall into a category known as super-Earths or subneptunes, planets larger than Earth but smaller than Neptune. These planets are thought to be some of the most likely candidates for water-rich worlds. Their size and density suggest that they may have large amounts of water, potentially covering their surfaces or existing as thick layers beneath the atmosphere. For example, the exoplanet Kepler-22b, located in the habitable zone of its star, is believed to be a super-Earth with a significant amount of water. It could be a water world with deep oceans, or even an ice-covered surface hiding an ocean beneath. Similarly, GJ-1214b, a subneptune just 40 light-years from Earth, has been studied extensively for signs of water. While its atmosphere remains mysterious, scientists believe that its density suggests a water-rich interior, possibly with a thick atmosphere of steam. These super-Earths and subneptunes represent some of the most promising candidates for finding water-rich worlds outside our solar system. As we continue to study their atmospheres and surfaces with new technology, we may soon discover signs of water, and possibly life, on these distant planets. The search for life on water-rich planets. Water is the key ingredient for life as we know it, and finding these worlds is one of the most promising signs that planets might harbor life. While Earth is the only known planet where life exists, the discovery of water-rich planets opens the possibility that life could evolve in environments very different from our own. On water worlds, life might take on forms that we can scarcely imagine. Instead of land-based ecosystems, entire biospheres could exist in the oceans, from surface-dwelling microorganisms to deep-sea creatures that thrive near hydrothermal vents. These planets might lack the familiar structures of mountains and forests. Water-rich planets, oceans beyond Earth. Water, the foundation of life we know it, is not unique to Earth. In the vastness of the cosmos, scientists believe there are entire planets where water not just present, but abundant. These water planets, sometimes referred to as ocean worlds, represent some of the most intriguing destinations in the search for life beyond our solar system. Imagine worlds where oceans stretch unbroken from horizon to horizon, where the land, if it exists at all, is submerged beneath column liquid water. These alien oceans, while familiar in substance, could hold secrets and surprise far beyond our understanding. The signs of water worlds. Water-rich planets are believed to have formed in the colder, outer region of their planetary systems, where water ice was plentiful during the formation of the planet. These worlds may have migrated closer to their stars over time, bringing their vast reservoirs of water with them. Unlike Earth, where water covers roughly 70% of the surface, but remains relatively shallow in comparison to the planet's overall size, water-rich planets may be dominated entirely by deep oceans. Oceans that could be hundreds, even thousands of kilometers deep. In these worlds, water will be a fundamental part of the planet's structure, creating unique layers of ice and liquid depending on the temperature and pressure. Beneath the vast surface oceans, immense pressure deeper level would force water into different forms, such as hot pressure ice, which is not the frozen water we know, but denser, more solid form ice that can exist even at high temperatures. This layering effect could create entire ocean ecosystems where life might find in environments more extreme than anything found on Earth. Some water-rich planets may even contain an ice mantle, a layer of ice beneath the liquid water, formed by the immense pressure of the overlying ocean. Such planets still have active geological processes below this ice mantle, similar to Earth's mantle and core. In these cases, hydrothermal activity could occur where the planet's internal heat causes cracks in the ice, releasing heat and chemicals into the deep oceans above. Such environments would be similar to Earth's deep-sea hydrothermal vents, where life thrives despite the absence of sunlight. Oceans that cover the world. Imagine standing on the surface of one of these planets, if you could. The view would be unlike anything you've ever seen, an endless expanse of water stretching out in every direction with no land in sight. The atmosphere might be thick with moisture, constantly feeding the ocean below with rains, or creating immense clouds that hover above, reflecting the light of a distant star. The color of water could vary depending on the planet's chemistry and the light of its sun, from deep blues to greens, or even darker hues, colored by unknown elements or biological life lurking beneath. These water worlds could have unique weather systems, driven by the interaction between the ocean and atmosphere. Without land to break up their patterns, massive storms could form, with wind and waves far more intense than anything we see on Earth. On some water-rich planets, superstorms could last centuries, driven by constant heat exchange between the ocean and atmosphere, creating monstrous waves and towering clouds that spiral across the surface. The deeper oceans would likely be completely alien environments. On Earth, our deepest oceanic trenches extend about 11 kilometers below the surface, but on water planets, these depths could be multiplied many times over. At such depths, light from the surface would be entirely absent, creating a dark, pressurized world without forms of life could evolve. Chemosynthesis, the process where life forms derive energy from chemicals rather than sunlight, could be widespread, just as it is at Earth's deep sea vents. The creatures on these planets, if they exist, may yet to live in complete darkness and under incredible pressure. They could be unlike anything we've ever encountered. Large, slow-moving organisms that glide in the deep waters, or entire ecosystems based on floating microbial life drifting just below the surface. The possibilities of life on such planets are vast and as yet unexplored. The atmospheres of water-rich planets. The atmosphere of a water-rich planet will be an essential factor in determining its habitability. In many cases, water worlds may have dense, thick atmospheres rich in water vapor, creating a greenhouse effect that keeps the surface warm and stable, even if the planet's far from its star. The James Webb Space Telescope and other future missions will allow us to study the atmospheres in detail, searching for signatures of water vapor, clouds, and other gases that indicate the presence of oceans and life. On some water-rich planets, the atmosphere could be in constant flux. The vast ocean contribute to rapid evaporation, creating an atmosphere heavy with moisture. This moisture condenses in mass cloud systems that circle the planet, creating endless rainstorms and contributing to the planet's dynamic weather. In some cases, these atmospheres could be soaked with water vapor that create a steam world. The surface is boiling ocean of water vapor and liquid, surrounded by towering clouds. In more water-rich planets, the atmosphere might resemble Earth's, with a balance of nitrogen, oxygen, and water vapor, possibly rise to clouds, rain, and even snow. However, the land and other systems could mean the entire planet is subject to frequent and powerful storms, with winds and waves far stronger than anything seen on Earth. In terms of habitability, the presence of liquid water is a key factor, but the atmosphere also needs to protect the surface from harmful radiation and provide a stable environment for life to thrive. Water planets orbiting and dwarf stars, which are known for their intense flares and radiation, we need a thick, protective atmosphere to shield the oceans from these bursts of energy. In some cases, the thick atmosphere of a water world could help regulate temperatures and protect against such radiation, allowing life to evolve in the oceans below. Europa, Enceladus, and the ice moons, clues from our own solar system. While exoplanets with vast oceans are a tantalizing prospect, we don't have to look far from home to find examples of potential water-rich worlds. Some of the most intriguing candidates for oceans beyond Earth lie within our own system. On moons Europa and Enceladus. Europa, one of Jupiter's largest moons, is covered in a thick gel of ice. Beneath the icy crust, scientists believe there is a global ocean of liquid water, kept warm by tide forces from Jupiter's gravity. The Europa Clipper mission, set to launch later this decade, aims to investigate Europa's ocean, searching for clues about its composition and whether it might harbor life. If Europa's oceans contain hydrothermal vents or other sources of chemical energy, it could be a prime location for extraterrestrial life, living in the dark, cold water beneath the ice. Similarly, Enceladus, a small moon of Saturn, has captivated scientists since the discovery of water-ice plume shooting from the South Pole. These plumes, which contain organic compounds, are thought to originate the surface ocean beneath the moon's icy crust. The heat required to keep this ocean from freezing comes from geological activity, similar to what we see Earth's near hydro vents. These plumes have been sampled by the Cassini spacecraft, and findings suggest that Enceladus could be another potential for life. While these moons are much smaller than the exoplanets we imagine, they offer clues of how water-rich worlds might form and behave. Studying Europa, Enceladus, and other ocean moons gives us a blueprint for understanding how deep oceans can exist in environments far from the warmth of the sun and how life might thrive in such extreme conditions. Super-Earths and sub-Neptunes, likely water-rich planets. Many of the exoplanets discovered by the Kepler Space Telescope and other missions fall into a category known as super-Earths or sub-Neptunes, planets smaller than Earth but smaller than Neptune. These planets are thought to be some of the most likely candidates for water-rich worlds. Their size and density suggest that they have large amounts of water, potentially covering their surfaces or existing as thick layers beneath the atmosphere. For example, the exoplanet Kepler 22b, located in the habitable zone of the star, is believed to be a super with a significant amount of water. It could be a water-rich world with deep oceans, and an surface hiding beneath. Similarly, GJ 1214b, a sub-Neptune 40 light years from Earth, has been studied extensively for signs of water. While the atmosphere remains mysterious, scientists believe that its density suggests a water-rich interior, possibly with a thick atmosphere of steam. These super Earths and Neptunes represent some of the most promising candidates for finding water-rich worlds outside our solar system. Continue to study their atmospheres and surfaces with new technology. We may soon discover signs of water and possibly life on these dim planets. The search for life on water-rich planets. Water is the key ingredient for life as we know it, and finding it on the world is one of the most promising signs that these planets might harbor life. While Earth is the only known planet where life exists, this study of water-rich planets opens up the possibility that life could evolve in environments very different from our own. On water worlds, life might take on forms that we can scarcely imagine. Instead of land-based ecosystems, entire biospheres could exist in the oceans, from surface-dwelling microorganisms to deep-sea creatures that thrive near hydrothermal vents. These planets might have familiar structures of mountains and forests. Of water worlds, we stand on the edge of discovery, looking out into the cosmos and asking one of the most fundamental questions: where else might life exist? Water, the key ingredient for life as we know it, is not confined to Earth. It's out there, scattered across the universe, forming the oceans of distant alien worlds. These water-rich planets, also known as water worlds, invite us to imagine life far from the shores of Earth, in places where water doesn't just float in lakes, it dominates the entire planet. A water world is a place where liquid water covers nearly the entire surface, or lies just beneath a thick layer of ice. These planets form in regions of space rich in water ice, and over time, through planetary migration and gravitational interactions, they find themselves closer to their stars, where the ice melts into vast, deep oceans. It's a process that began in our own solar system, with the icy moons of Jupiter and Saturn, and extends to the exoplanets we are now just beginning to discover. Oceans deeper than imagination. On Earth, the ocean's deepest point, the Mariana Trench, plunges nearly 11 kilometers below the surface. Yet on a water world, oceans might extend hundreds, even thousands of kilometers deep. Imagine a planet where water doesn't stop shallow depths, but continues downwards through layers upon layers of weight, until pressure becomes so great that the water itself changes form. At these immense pressures, water enters what we call high-pressure phases. It sounds counterintuitive. Ice forms in an environment of immense heat and pressure. But under these extreme conditions, water solidifies in forms that we don't see on Earth, creating types of ice that are more dense than the liquid above. This layering, liquid water on top, high pressure ice below, could shape the entire geology of a water world. On Earth, tectonic plates move over a molten mantle, creating the dynamic geology we are familiar with. But on a water world, these tectonic plates might instead glide over a layer of ice, with no land masses bathed through surface to form continents. Instead, an endless world-span ocean would stretch out in all directions, the liquid surface forming the only landscape. Beneath the surface, deep in the abyss where no sunlight penetrates, life may exist in environments shaped by chemical reactions and internal heat rather than sunlight. Just as life thrives at Earth's deep-sea hydrothermal vents, where organisms draw energy from the Earth's internal heat rather than the sun, life on water worlds might exist in deep, hidden ecosystems. These could be entirely different from anything we've ever seen, yet bound by the same chemistry of life: carbon, water, and energy. Atmospheres, climate, a world of constant change. These oceans don't exist in isolation. The atmospheres of water worlds play a crucial role in determining the planet's climate, the potential for habitability. A thick atmosphere, rich in water vapor, could develop the planet, creating a runaway greenhouse effect that traps heat, warming the surface, and potentially turning the entire planet into a steam world. A place where the surface is not liquid water, but an ocean vapor. These steam worlds may still have oceans beneath their dense atmospheres, but reaching would require descent through thick clouds of steam, where temperatures and pressures soar. On a more temperate water world, the atmosphere might resemble Earth's, with boundless amounts of water vapor, nitrogen, and possibly oxygen. These planets experience dynamic weather systems, constant rainstorms, powerful winds, and enormous cloud formations that swirl across the surface, fed by the endless supply of water. Without land to break up the patterns, storms might grow larger than any we've seen on Earth. Superstorms last for years, driven by the interaction between the atmosphere and the ocean below. The interaction between the atmosphere and ocean could also create deep circulation patterns, where warm water from the surface sinks into the depths, while cooler water rises in upwelling currents. These movements would influence not just the climate, but potentially ecosystems within the oceans, providing nutrients and energy to sustain life throughout the water. A silent, hidden world. The greatest mystery of water worlds lies beneath their waves. What kind of life could exist in a world without land? Could life on such planets evolve in the same way it did on Earth, where land-dwelling species diversified and adapted? Or would the ocean be the only environment these life forms ever know? In the deep, dark oceans of a water world, sunlight might be a distant memory. If a planet is far from its star, or if the atmosphere is too thick, no light would reach the depths. Life in these oceans would need to rely on chemosynthesis, a process where energy is derived from chemical reactions rather than sunlight. On Earth, chemosynthetic bacteria thrive near hydrothermal vents, drawing energy from the chemical compounds emitted by the planet's internal heat. On a water world, life might evolve to take advantage of similar processes, existing in isolated pockets near sources of geothermal activity. Heat and chemicals rising from the planet's core, warming the deep ocean and providing the raw materials for life. But these environments could also present their own challenges. The lack of sunlight and photosynthesis, one of the fundamental odds for life on Earth, would not be possible, and life might evolve in ways that we can't predict. Complex ecosystems could exist in these hidden depths, entirely separate from the surface world, where the interplay of heat, chemicals, and pressure create unique conditions for survival. The surface water world. With missions like the James Webb Space Telescope, we are now closer than ever to finding these water worlds. To prepare for observation of distant stars, we can distinguish that fall within the habitable zone. Being around a star where conditions are right for liquid water to exist. We can analyze life in places that pass through their atmospheres, searching signs of water vapor, clouds, or gases might be presence of oceans. In our own solar system, the icy moons of Europa and Enceladus. There are hidden oceans beneath thick layers of ice. For tantalizing clues about what water worlds might look like. These moons may harbor liquid oceans, warmed by the internal heat of their parent planets, and scientists are eagerly awaiting the results of upcoming missions like Europa Clipper, which will explore these icy moons in detail. But the search for water-rich exoplanets takes us even farther home. Planets like Kepler, G2b, or GJ14b are prime candidates for water worlds. Super Neptunes with thick atmospheres and lower densities, suggesting the presence of vast amounts of water. These planets are located in habitable zones of their stars, meaning that liquid water exists on their surfaces. If there are indeed water worlds, they hold key to understanding how life is in the universe and what form life might take. Life beneath the waves. As we continue our search for life beyond Earth, water worlds represent one of the most promising environments to explore. With vast oceans, complex climates, and unique geological processes, these planets harbor life in forms that are completely alien to us. Life on a water world might never no land. But it could thrive in the darkness and presence and only begin to imagine. Study of water worlds, we are expanding our understanding of what life can be, how it might adapt, evolve, and survive in environments far different from our own. In the depths of these oceans, we may woke, and every new planet brings us closer to those answers. So, join us as we journey through the cosmos, uncovering the mysteries that lie beyond. If you did the journey through space and want to stay updated on the latest in space exploration, subscribe to our channel and hit the notification bell so you never miss a video. There's a whole universe out there waiting to be explored, and we want you to be part of it. Thanks for watching. Looking out, we're no longer bound to alone. Our planet drifts quietly beneath us, a cradle of life suspended in the vastness. But beyond, just past that window, the story of space unfolds, not just in moments of birth, in whispers of a distant world and the secrets they hold. There, in darkness, we can trace the outline of Sputnik, humanity's first tentative step in cosmic sea. It was more than just a satellite. It was the beginning of an idea. The idea that our future, our destiny, was out there, somewhere in the stars. And while that was the start, it was only the beginning of what would be the deep exploration of the universe. In time, the window opened wider. We glimpsed Yuri Gagarin, the first human to see Earth from space, to feel the pull of the planet fall away as he soared above the curvature of the globe. The stars beyond him were not just points of light, but destinations, uncharted, waiting for discovery. He carried with him not just the weight of history, but the curiosity of every person on Earth who had ever wondered what lay beyond the atmosphere, beyond the pale blue. And then, as the years unfolded, the window revealed new scenes. The grainy footage of Neil Armstrong and Buzz Aldrin stepping onto the moon, their footprints pressed into the dust of another world. It was a single moment of presence on the moon, but it echoed across time, filling us with wonder and possibility. These human journeys into space weren't just missions. They were the first stanzas in a long, unfinished poem about exploration, about seeing what was beyond the next horizon, the next planet, the next star. Through this window, we see not just the destinations we've reached, but the unanswered questions that linger in the night sky. As an astronomer, I often find myself looking beyond the visible stars, past the familiar places like our moon, or Mars, or the icy moons of Jupiter, to the countless exoplanets scattered across the Milky Way with oxygen, or perhaps the faint signature of life, the Kepler Space Telescope. But we are not only looking outward from this window. Space history has also taught us to reflect on our place in the universe. Every satellite, every astronaut, every telescope reminds us that Earth is fragile, that life, this precious, miraculous phenomenon, exists within a delicate balance. Our exploration of space has shown us that we are connected, not just each other, but to stars themselves. And from this window, we can also see future. Mission that will one day take us perhaps to Mars or even beyond. The James Webb Space Telescope, poised to peer deeper into the cosmos than ever before, may reveal the atmospheres of distant exoplanets, perhaps even signs of life. It will show us new parts of space history, things we cannot yet imagine. Questions beyond the asked. Space history is not a distant memory, but a living, breathing story. one we are writing with each new discovery, with every question we dare to ask. As I look out from this window, I see not just the stars, but the echo of the past, the whisper of future journeys, and the certainty that we are only at the beginning of our exploration. The universe is vast, and mysteries boundless, and we, our ancestors who first gazed up at the sky, are only just beginning to understand our place within it. The stars shimmer beyond, vast and endless. Yet within that boundless expanse lies the record of first humble steps toward infinite. Each of those steps, Sputnik, Gagarin, Apollo, carries with it the pulse of human curiosity. Let us try to understand not just where we are, but where we might one day go. That same drive, pushing us to peer deeper into the cosmos, and brings us to the precipice of new discoveries, as we turn our gaze not into the stars, but to the world waiting. Through this window, I think of the world we've yet to see with our own eyes. The exoplanets hidden in the light of distant stars. Planets won't begun to detect by watching a star dim ever so slightly as they pass in front of them. These are the new frontiers of space history. Planets, oceans, clouds, and atmosphere filled with chemical signature of life. Take contrast one system with seven rocky planets, circling a cool, dim star. From our vantage point, TRAPPIST, one is just a flicker of light in the constellation race. Through the lens of our instruments, it becomes a vibrant system full of potential, with planets locked in a delicate gravitational dance. What would it be like standing on one of those worlds, looking up at the sky, and see 6 other planets, large as moons, hanging overhead? This is a new space history unfolding. Unlike the moon or Mars, places we've dreamt of walking on, these exoplanets are so distant that even with our fastest spacecraft, they remain unreachable for now. But through telescopes like Kepler, TESS, and the upcoming James Webb Telescope, we are beginning to unravel their mysteries. We can detect their atmospheres, search for water vapor or methane, and speculate whether they are bathed in sunlight or trapped in eternal night. When I look out from this window, I see not just the future, but the delicate balance that connects all of this. How magnetic fields shape stellar winds, how starlight breaks through exoplanetary atmospheres, how the chemistry of a distant world might tell us if life is taken there. These aren't just idle thoughts. They're the questions that define the next chapter of space history. And yet, there's always awareness that we are the early pages of history. Space telescopes we launched at the beginning. They've shown us the possibility that there are thousands, maybe millions of planets out there like Earth, orbiting their stars at just the right distance for life to flourish. These planets hold the key to answering one of the oldest questions humanity has ever asked. Are we alone? It's incredible to think that the light from those distant worlds, as it passes through our spheres, is bringing us answers, slowly, quietly, but surely. That light, especially observed, carry the fingerprint of life or the lack of it, bringing the absorption lines of gases like oxygen, water, and carbon dioxide. But beyond the science, beyond the there's something deeply human about this view. We've always looked outward, to the stars, for inspiration and wonder. Now, through the lens of our telescopes and the windows of our spacecraft, we're seeing more than just the faraway stars and planets. We're seeing seeds of our future. Maybe one day, not too far from now, send missions to some of these exoplanets. Perhaps we'll find one oceans and real air. A place feels strangely familiar in its distance. Maybe we'll look back on this time from a future spacecraft orbiting one of these distant worlds and think how far we've come. We'll remember the nights spent gazing up stars, wonder if there was without there. We'll realize we were already part of something larger, something cosmic. From this window, we are part of space history, and it's still being written. Every discovery, every exoplanet we identify, brings us closer to the possibility that we're not alone in this universe. The future of space history is unfolding just beyond our reach, in the absolute distant world and starlight that traveled millions of years to meet our eyes. Space history is not just about the past or the future. It's about the now, the moment we're in, where our imaginations meet the reality of the cosmos. But more than that, beyond the history that we've written so far, we glimpse worlds that bend us forward. Beautiful worlds, strange and wondrous, each with its own story, waiting to be discovered. Through this window, we imagine planets bathed in the light of red suns, skies painted in hues we've never seen on Earth, world like Proxima Centauri b, orbiting the closest star to our own, tantalizingly within reach. Perhaps a place where oceans lap against alien shores under a dim crimson sky. Proxima Centauri, our nearest exoplanetary neighbor. Proxima Centauri b, the closest known exoplanet to Earth, orbits star Proxima Centauri, red dwarf located just 4.24 years away in the Alpha Centauri star system. Discovered in 2016 by the European Observatory ESO, using the radial velocity method, Proxima Centauri b quickly became one of the most exciting exoplanets ever found. Not only is it close in astronomical terms, practically in our cosmic backyard, but it also lies in the habitable zone of its star, meaning conditions could potentially allow for liquid water on its surface. This discovery makes Proxima Centauri be a prime candidate in the search for habitable worlds beyond Earth. Proxima Centauri b was discovered by measuring slight wobbles in the movement of the parent star. The planet has a minimum mass of about 1.17 times that of Earth, classifying it as an Earth-like planet or a super-Earth. Its orbital period is about 11.2 days. Being able to full orbit around its star much faster than Earth does around the Sun. Despite its close orbit, Proxima Centauri b lies within the habitable zone, the region around a star where temperatures could allow for liquid water, a key ingredient for life. Because Proxima Centauri is much cooler and dimmer than the Sun, its habitable zone is located closer to the star. Proxima Centauri b orbits a distance of about 5 cents astronomical units, only 5% of the distance between Earth and the Sun. Doesn't sound real close. The reduced luminosity of Proxima Centauri means the planet receives roughly the same starlight that Earth does from the Sun. A tidally locked world, one of the most intriguing, yet challenging aspects of Proxima Centauri b is the likelihood it's tidally locked. This means that one side of the planet constantly feeds its star, while the other side remains in perpetual darkness, much like Moon's relationship with Earth. If Proxima Centauri b is indeed tidally locked, it will have extreme temperature variation between its day side and night, with one hemisphere receiving continuous sunlight and the other shrouded in eternal darkness. This side could be blisteringly hot, with direct exposure to Centauri's radiation, while that side might be freezing cold. However, in the zone, the region between the day and night sides, temperatures might be more moderate, potentially creating habitable conditions. In this twilight region, liquid water might exist, and life, if present, could potentially thrive in this narrow band conditions are more stable. If Proxima Centauri b has a thick atmosphere, it could help reach the heat from the day side to the night side, reducing the temperature extremes. In this scenario, atmospheric circulation play a crucial role in shaping planet's climate, allowing for more uniform temperatures across the surface. Oceans, if they exist, also help moderate the climate by transporting heat, making the planet more hospitable for life. The possibility of atmosphere. Whether or not Proxima Centauri has an atmosphere is one of the questions regarding its potential habitability. A thick atmosphere would not only help moderate the planet's climate, but it could also protect the surface from harmful stellar radiation. However, the stellar flares from Proxima Centauri can have significant consequences for the planet's atmosphere, potentially stripping away over time. Stellar flares emit high-energy particles and radiation that can corrode a planet's atmosphere, particularly on planets orbiting close to their star, like Proxima Centauri b. Without a strong magnetic field or protective atmosphere, Proxima Centauri could be exposed to harmful radiation, making it difficult for life to survive on the surface. Despite these challenges, some also suggest that Proxima Centauri might have retained its atmosphere, possibly due to a strong magnetic field or other protective factors. If the planet does have an atmosphere, it will be key to understanding its potential for habitability. Future missions and telescopes, such as the James Webb Space Telescope, may be able to study the atmospheric composition of Proxima Centauri, provide data about its environment. Proxima Centauri's flares and impact. One of the major hurdles to life on Proxima Centauri b is the intense stellar activity parent star. Proxima Centauri, like many red dwarfs, regularly emits stellar flares, bursts of radiation that can dramatically increase the amount of ultraviolet and X-ray radiation hitting the planet. These flares encircle the atmosphere and damage any potential biosphere. The 2017 observation captured one of the largest flares ever seen from Proxima Centauri, which temporarily increased the star's brightness by a factor of one. Such flares, if frequent, could be devastating for a planet like Proxima Centauri b. However, some scientists believe that if the planet has a sufficiently thick atmosphere or a strong magnetic field, it could still retain habitability in certain regions. One possibility is that life on Proxima Centauri is of ice. Beneath the surface, in the depths of the ocean or within the planet, life could thrive to survive in extreme conditions, shielded from the radiation above. Microbial life, similar to the extremophiles that survive in Earth's harshest environments, could be the dominant form of life here, clinging to the narrow curiosity. It's a target to Earth means that it's one of the few we may be able to study in detail within our lifetimes. Future missions to the Alpha Centauri system, combined with next-generation telescopes, may allow us to determine once and for all whether this planet is habitable or even inhabited. Could we one day walk there, feel the faint warmth of a different star on our skin, and look up to see unfamiliar constellations? Then there is Kepler 452b, a world that has been called Earth's cousin. Orbiting in the habitable zone of a star much like our Sun, Kepler 452b might be covered in green, its landscape lush and fertile, with thick clouds drifting lazily above a landscape of towering mountains and deep valleys. There perhaps rain falls just as it does here, nourishing life that grows and evolves, untouched by human hands but connected to us by the same cosmic forces that shaped our own Earth. It will circle distant stars like LHS 1140, a rock planet just 40 light years away. Its gravity might be stronger, the air heavier, with an atmosphere rich in possibilities. Perhaps dense clouds swirling across a cobalt blue horizon, winds carry sand, alien oceans, thick with light you have yet to imagine. The light there might be faint, a soft glow from its red dwarf star, casting the landscape in perpetual twilight. A world forever on cusp of dawn or dusk. In contrast, one system, Sabaki worlds, orbit cool, dim star, each unique and beautiful in its own right. Imagine standing on one of those planets, with the other 6 hanging low in the sky, like moons. The sunsets there might be like nothing we've ever seen. Purple skies fading in amber, with bands of starlight filtering through the thin atmosphere. What life could thrive in such a place? Under the gentle glow of an ultra-cool star, where days stretch long and the warmth is ever so faint. Beyond the star we know, there are surely worlds that defy all expectations. Planets where seas of methane glisten on emerald skies, or where clouds of ammonia rise high above mountain ice. There could be gas giants with moons as beautiful and varied as the planets themselves. Some covered in tropical storm that rage for centuries. Others with crystal clear oceans that reflect the stars as though they're mirrors. And there may be water worlds, entire planets covered in oceans, with endless waves stretching from horizon to horizon, warmed by the sun, teeming with life and death. One can only dream of the beauty of a world like Gliese 581G, an exoplanet that orbits its star in the habitable zone, where the temperature is just right for living water. Perhaps this world is cloaked in mists, its surface obscured from our distant gaze, a place where life flourishes in the watchful eye of the red sun. Trees with leaves dark as night might stretch toward the sky, gathering every last photon of light, while rivers of crystal clear water carved pass through fertile plains, home creatures as varied and wondrous as the ecosystems of Earth. Gliese 581G, a potentially habitable exoplanet. Gliese 581G is one of the most intriguing exoplanets ever discovered, orbiting stars just 20 light years away from Earth. Found in 2010 by astronomers using the Keck Observatory in Hawaii, Gliese 581G quickly captured the imagination of scientists and space enthusiasts alike because it lied in what known as the habitable zone, around a star where conditions may be just right for liquid water exist. This discovery led to speculation about whether Gliese 581G support life, making it a focal point in the search for Earth-like exoplanets. The star, Gliese 581. Gliese 581G orbits a star called Gliese 581. A red dwarf located in the constellation Libra. Dwarfs are smaller, cooler, and much dimmer than our sun, but they're the most common type of star in the universe. Despite being much less luminous, red dwarfs often have long, stable lifespans, meaning planets orbiting them could enjoy relatively stable conditions for billions of years, an important factor in the potential for life to develop. Gliese 581, like many red dwarfs, is a star that exhibits stellar flares, sudden bursts of energy that can release powerful radiation. This type of activity could be a challenge for habitability, particularly for planets close to the star. However, because Gliese 581G lies right in the middle of the habitable zone, there is hope that its atmosphere, if it exists, could protect the planet from such radiation, creating a stable environment. The discovery of Gliese 581G. The discovery of Gliese 581G was made by analyzing the radial velocity of the star, essentially, how the star wobbles due to the gravitational pull of orbiting planets. This technique allowed astronomers to detect multiple planets in Gliese 581 system, including Gliese 581G, which was found to orbit in the star's habitable zone. The planet itself is estimated to be a super-Earth, meaning it is larger than Earth, but smaller than gas giants like Neptune. Gliese 581g was initially thought to be about 3 to 4 times the mass of Earth, with a radius about 1.5 times larger than our planet. Its year, one complete orbit around its star, takes just 37 days, meaning it is much closer to Gliese 581 than Earth is to the Sun. However, because Gliese 581 is a dim red dwarf, this proximity places Gliese 581g right in the sweet spot of the habitable zone, where temperatures could allow for liquid water to exist on its surface. Could Gliese 581g support life? One of the most exciting aspects of Gliese 581g is its potential to harbor liquid water, which is considered essential for life as we know it. If Gliese 581g has an atmosphere, it could act as an insulating layer, helping to regulate the planet's temperature and possibly allow for oceans or lakes of liquid water. However, there's an important caveat: tidal locking. Like many planets orbiting red dwarfs, Gliese 581g is likely tidally locked, meaning one side of the planet is always facing the star, while the other side is in perpetual darkness. This could result in extreme temperature differences between the day side and night side. The side facing the star might be extremely hot, while the dark side could be freezing cold. But between these two extremes, there could be a twilight zone, a region where temperatures are moderate enough to allow for liquid water and potentially life. In this twilight zone, temperatures could be mild, and if there is water, it might flow in the form of rivers or pool into lakes or seas along the boundary between light and dark. The presence of an atmosphere would be key here. A thick enough atmosphere could help distribute heat around the planet, creating a more temperate climate across a large region, rather than just the boundary. The possibility of an atmosphere. To date, we don't know whether Gliese 581g has an atmosphere, and that remains one of the planet's greatest mysteries. It has a substantial atmosphere. It could protect the surface stellar flares emitted by Gliese 581 and help regulate planet temperature. The atmosphere could also provide clues to the possibility of life. If we're able to observe the planet atmosphere in detail, we look for signs such as water vapor, oxygen, methane, and carbon dioxide. These gases are associated with the processes of life on Earth. Their presence on Gliese 581g could be a process sign of biological activity. However, even without these specific markers, an atmosphere that provides the right conditions for liquid water would be an exciting story. In the absence of an atmosphere, Gliese 581g would likely be a barren, inhospitable world, without atmospheric pressure to keep water in liquid form. Any surface water would either freeze solid on the dark side or evaporate into space on the day side, making the planet unlikely to support life as we know it. The controversy. Despite the initial excitement, the existence of Gliese 581g was later called into question by some astronomers. In 2014, new data suggested that what appeared to signal Gliese 581g might actually be caused by stellar activity, specifically magnetic activity on the surface of the star. This stirred debate within the scientific community, with some researchers arguing that Gliese 581g's discovery could fall positive. However, the controversy did not fully close the case on Gliese 581g. Some astronomers still believe the planet exists, but that more detailed observations are needed to confirm its presence. The Gliese 581 system remains prime target for further study of planets in this system, including Gliese 581d, also near the habitable zone, making it one of the most promising nearby star systems to search for habitable worlds. The future of Gliese 581g exploration. While Gliese 581g's status remains uncertain, it highlights the challenges and excitement of discovering potentially habitable exoplanets. Future telescopes, such as the James Webb Space Telescope, are expected to bring us much closer to understand distant worlds like Gliese 581g. These instruments will be able to analyze the light passing through exoplanet atmospheres, providing detailed information about their composition and structure. In the case of Gliese 581g, one of the most important steps would be to confirm its existence and then focus on determining whether it has an atmosphere. If we find that it does, the next step would be to search for signs of habitability. ability, such as the presence of water vapor or other biosignatures. Even if Gliese 581g proves not to exist, the search for Earth-like exoplanets in the habitable zones of nearby stars will continue. Red dwarfs like Gliese 581 are prime targets because their small size and cooler temperatures forever bathed in light and the upshot internal darkness. In the twilight zone, the sky glows a pale orange or red hue, reflecting the soft, dim light of the red dwarf star. The landscape might be rocky and barren in places, but along the edge of the light, liquid water could flow in rivers collected in seas. The air could be dense with moisture, stormy patterns that balance the extreme temperatures between the two sides of the land. As you look toward the horizon, you might see storm clouds gathering, or even drives intense weather systems. Behind you, the sky fades into deep darkness, the stars glimmer coldly over the landscape. Life, if it exists, might link to the borderlands, where the balance of light, water, and temperature creates just the right conditions for survival. In the search for life beyond Earth, Gliese 581g remains one of the most fascinating and enigmatic possibilities. Whether it proves to be a real planet or just a false signal, its discovery has opened our eyes to the potential of the universe, showing us that the ingredients of life could be scattered across the cosmos, waiting for us to find them. And what about the mysterious water-rich planets that might exist in abundance? Imagine a planet where entire continents float on vast, deep oceans, their surfaces dotted with archipelagos of glowing bioluminescent life. Beneath the waves, ancient creatures swim through the depths, their movements slow and graceful, as if the oceans themselves read time to tide the distant star. The skies above the water might shimmer with their auroras, caused by magnetic fields far more powerful than anything we know on Earth, creating dazzling displays of light as particles from parent stars interact with planet's atmospheres. Perhaps the most beautiful worlds are those that challenge our understanding of what life is. Planets that orbit binary stars, where two suns cast overlapping shadows, creating twilight zones where life might flourish in a delicate balance of light and dark. The landscapes of these worlds could be otherworldly, sand dunes stretching under two suns, with deep canyons carved by the winds that howl through them. Or perhaps the surfaces dotted with glassy lakes that reflect both stars, their surfaces rippling in the wind like pools of liquid light. As we look out from this window, we are filled with a sense of awe and possibility. The universe is not a cold, empty place, but a canvas filled with vibrant worlds, each one with its own unique beauty and its own story to tell. The light from these distant planets has traveled for thousands, millions, even billions of years to reach us. And as we study that light, we begin to understand that the beauty of the universe is far more complex and diverse than we ever imagined. Each of these worlds, seen or unseen, represents a new chapter in the story of space exploration, a chapter that humanity has only just begun to write. We have sent our robotic explorers to the edges of our own solar system, but the real journey is just beginning. With each new telescope, each new mission, we are opening windows into new worlds, revealing the wonders of the universe one planet at a time. These beautiful worlds, with their alien sky decoration, we catch glimpses of systems and the planets that might orbit within them, revealing a universe far more intricate than what's meant. A cosmic dance of light and gravity. At first glance, binary stars may appear similar to solitary stars we're familiar with, like our own Sun. But these pairs of stars are locked in a delicate dance, their gravitational pull keeping them in constant motion around one another. This movement is a cosmic ballet. The stars orbit a common center of mass, sometimes so close they nearly touch, and other times separated by vast distances. Binary star systems are composed of stars of similar size and brightness, while others are more extreme, with one star much larger or more mass in its partner. These contrasting pairs, like the supergiant binaries, create extraordinary contrast in their interactions. Massive, radiant stars pulling their smaller companions with such force that their outer legs are sometimes stripped away, feeding the large stars insatiable energy. Binary stars can vary in their proximity and relationship to each other. Closed binaries orbit in such tight proximity that they can exchange material, often resulting in dramatic stellar phenomena like novae, or even the eventual merger of the two stars into a single, more massive one. In contrast, wide binaries may orbit at distances so big they take thousands of years to complete a single illusion, appearing more like two independent stars from observers' perspective. These wide systems can have planets orbiting one or both stars in intricate orbital resonances, creating a complex and dynamic environment for a planetary system. Two suns in the sky. The worlds of binary stars. One of the mesmerizing ideas about binary stars is imagining what it would be like to live on a planet orbiting such a system. Picture a sky of two suns, each casting its own unique light across the landscape. In some binary systems, one sun may be larger and brighter, dominating the day, while the other is smaller, offering a softer, secondary light that waxes and wanes as the stars move through their orbit paths. The size of such a world would shift dramatically, with a dance of suns creating days and nights that vary in brightness and length. Some planets may both start what is called a combinary orbit, where the planet circles around the entire binary pair, much like the fictional planet Tatooine from Star Wars, which famously had two suns in the sky. These circumbinary planets must navigate the gravitational tug-of-war between two stars, creating highly stable orbits, in some cases chaotic, unpredictable paths in others. For a planet in such a system, real stars' motion can cause dramatic shifts in temperature and light, leading to seasons more extreme than anything we experience on Earth. In other binary systems, planets orbit just one of the stars while the second star orbits at a greater distance. These planets experience changes in their sky as the second star comes in view and fades away, potentially leading to periods of double sunrises or sunsets. Imagine standing on a planet like this, watching one sunset in the west, while the other hovers low on the horizon. Its light casts a soft glow long into the evening. Kepler 16b, a circumbinary planet discovered by the Kepler Space Telescope, is a real-world example of this. It was a pair of stars in constellation Cygnus, and its skies would be a stunning display of celestial choreography, with two suns rising and setting in sync with its orbit. The discovery of Kepler 16b was a watershed moment, proving that planets can indeed exist in stable orbits around binary star systems, opening up new possibilities where we might find habitable worlds. The science behind binary stars, interactions, and evolution. The relationship between two stars in a binary system can be as peaceful as it is violent. In closed binary systems, where stars are near enough to influence each other's evolution, a process known as mass transfer can occur. One of the stars in a closed binary begins to swell into a red giant at the end of its life. Its outer layer can spill over onto its companion. This can result in one star growing significantly in mass, while the other shrinks or even loses its outer layers entirely, becoming a white dwarf or non-compact stellar remnant. The most extreme version of the process occurs in compact binaries, where the two stars are so close they share a common outer envelope gas. These systems often unstable and can eventually merge into a single star, where they result in dramatic stellar explosions such as nova, when material from one star falls onto a white dwarf, leading to a thermonuclear explosion that briefly outshines an entire galaxy. In some cases, binary stars can end their lives in spectacular fashion. If both stars in the system are massive enough, they may both go supernova, leaving behind two neutron stars or black holes orbiting one another. These stellar rings continue their dance, spiraling closer and closer together as they lose energy in the form of gravitational waves. Ripples in space are predicted by Einstein's theory of general relativity, and for the first time, the LIGO Observatory in 2018. When two neutron stars or black holes finally collide, they release bursts of energy so powerful they can be detected across the universe. The ability of binary stars. Life in a dynamic sky. One of the most exciting questions surrounding binary stars is whether life could arise on planets or these systems. The complex gravitational interactions between two stars create unique environments. They do not necessarily exclude the possibility of life. In fact, binary systems may offer some advantages. For planets in circumbinary orbits, the gravitational pull of two stars can create highly stable orbital regions, known as habitable zones, where conditions might allow liquid water to exist on the surface. In such systems, the changing light of two suns can lead to fascinating variations in climate and weather, potentially giving rise to life forms adapted to fluctuating conditions. Planets orbiting just one star in the binary system must also experience periods of enhanced energy as the second star approaches, potentially boosting photosynthesis and other biological processes. Life on such worlds could evolve to take advantage of these cycles, thriving during the times when both stars' light reaches the planet's surface and entering periods of dormancy, reduced activity when one star recedes. However, binary star systems also present challenges. The complex gravitational dynamic in the planetary orbits is less stable, and the intense radiation from certain types of stars, such as red giants or massive stars, could pose significant hurdles to life. The discovery of planets like Kepler 47c, a gas giant orbiting a binary star, suggests that planet formation is possible in these systems, and where there are planets, potential for life remains. The next frontier, exploring binary systems. As we peer deep into the universe, the study of binary stars continue to play a crucial role in our understanding of stellar evolution and the search for habitable worlds. With the advent of advanced telescopes like the James Webb Space Telescope, we are poised to explore these systems in even greater detail. JWST will allow us to observe the atmospheres of planets orbiting binary stars, helping us determine whether these distant worlds could support life. Future missions could also send up to the Alpha Centauri system, the closest binary star system to Earth, located just over years away. Alpha Centauri consists of two stars, Alpha Centauri A and Alpha Centauri B, the possibility of fruit star Proxima Centauri, which has its own planet Proxima. These stars offer a tantalizing opportunity to study a binary system close and to explore the potential for habitable planets in our cosmic backyard. Place the window into the night sky. We realize that binary stars are not just astronomical curiosities, dynamic systems filled with potential for discovery. Whether the drama of stellar collisions, the gentle dance of two suns, the prospect of life under dual star system. Binary stars remind us that the universe is far more diverse and intricate than we ever imagined. They are a testament to the beauty and complexity of the cosmos, a cosmic dance of light, gravity, and time that continues to unfold before our eyes. Two suns in the sky, the worlds of binary stars. Imagine standing on the surface of the planet, and instead of one familiar sun hanging in the sky, there are two, each casting its own light, each pulling on the planet in its own way. In binary star systems, this isn't just science fiction, it's reality. For any planet that orbits two stars, the rhythm of day and night, the changing seasons, and even the color of the sky could be profoundly different from what we experience here on Earth. The worlds of binary stars offer a fascinating glimpse into the incredible diversity of planetary environments across the cosmos, where dual suns create landscapes, climates, and atmospheres unlike anything we've seen. The beauty of binary sky, planet orbiting a pair of stars in a circumbinary orbit. The sky would be in constant flux, influenced by the shifting positions of its suns. Depending on the distance between stars and planet, the two suns might rise and set together, or at different times, creating a spectacular dance of light. Imagine watching one sun dip below the horizon, casting long shadows across the landscape, while the other remains high in the sky, bathing everything in a warm, sunlight. The interplay between the two stars can paint the sky with colors unseen on Earth, brilliant oranges, deep purples, and even hues of green or red, depending on the spectral types of the stars involved. In some cases, the stars might be very different from one another. One could be a hot, bright blue star, radiating intense ultraviolet light, while the other is a cooler, dimmer dwarf. The star contrasts create fascinating effects on the planet's surface. The cooler star might create a softer, more diffuse light, while the hotter star shines with piercing brilliance. The dual light sources could cast overlapping shadows, creating a surreal landscape of shifting brightness and color. The changing positions of the suns could also create unique weather patterns. In some parts of the planet's orbit, both suns might shine equally bright, raising the temperature significantly, while in other parts, the stars could be farther apart in the sky, casting the planet into periods of cooler light. These fluctuations could lead to extreme seasons or even regions where one side of the planet is locked in perpetual twilight, while the other basks in daylight from both stars. The physics of circumbinary orbits. For a planet to exist around a binary star system, it must follow a delicate path. Circumbinary planets, those that orbit both stars, must balance the gravitational pull of two stellar bodies while maintaining a stable orbit. The region in which a planet can safely orbit is called circumbinary habitable zone, and it is shaped not only by the heat light of the stars, but also by gravitational interaction between them. In close binary systems, where the stars orbit each other tightly, the habitable zone for a circumbinary planet is typically farther out, where the planet can experience a more stable gravitational environment. In binary systems, the habitable zone can be closer to the stars, allowing for the possibility of plants that can sustain liquid water and potentially life. Planets that orbit both stars at a safe distance experience a unique but stable gravitational balance. The gravitational pull from each star creates a wobble in the planet's orbit. This wobble can settle into a rhythm that keeps the planet in a stable path around the binary pair. This means that while the gravitational forces are more complex than those of the planet orbiting a star, it's entirely possible for planets to exist in these systems for billions of years, long enough for life to evolve. Kepler 16b, as mentioned earlier, is a prime example of a circumbinary planet. It orbits two stars, a K-type and an M-type dwarf, both cooler and smaller than the Sun. While Kepler 16b is a gas giant and not likely to harbor life, its discovery was a major breakthrough, proving that stable planetary orbits can exist around binary stars. It's a confirmation that planets in such systems might be more common than we once thought. Seasons and climate on a circumbinary planet. On a planet orbiting two suns, the concept of seasons would be far more complex than on Earth. Seasons on our planet are caused by the tilt of the Earth's axis as it orbits the Sun, leading to variations in sunlight across the year. On a circumbinary planet, positions of the stars relative to one another create dual season cycles, influenced by the planet orbit around both stars, and they're caused by changing positions of stars in relation to each other. During certain parts of the year, the two suns might align, bathing the planet in double the amount of light and heat. This creates super summers, periods of intense warmth and bright light. Conversely, when stars are on opposite sides of their orbit, their combined light might be weaker, plunging the planet into cooler, dimmer seasons, what we might call superwinters. The ebb and flow of these dual solar influences would create complex climate patterns, perhaps even leading to exotic weather phenomena such as extreme wind patterns, fluctuating ocean currents, or rapid chain cloud formations. Some circumbinary planets might experience binary eclipses, where one star passes in front of the other. This can lead to brief periods where the planet is shaded from the light of one of the suns, creating a temporary cooling effect similar to an eclipse on Earth, but potentially lasting longer or affecting the entire planet. Such events have dramatic effects on the planet's ecosystem and climate, causing rapid shifts in temperature and light levels. The habitability of planets with two suns. One of the exciting prospects in the study of binary star systems is the potential for habitable planets, worlds with the right conditions for liquid water and life. While binary star systems were thought to be unlikely hosts for life, the discovery of binary planets like Kepler-Steen b and others has shown that these systems can indeed support stable planetary orbits. The question now is what any of these planets located in the habitable zone, where regional temperatures are just right for the water to exist. In binary systems where the stars are relatively small and cool, such as two dwarfs or a combination of an dwarf and a K dwarf, the habitable zone can be closer to the stars. In these systems, a planet in habitable zone might experience milder temperatures, with combined life in the two stars providing enough warmth for liquid water without overwhelming the planet with radiation. Conversely, in systems where one or both stars are much hotter and more massive than the sun, the habitable zone would be farther out, where the combined heat and radiation of two stars would be more balanced. These planets might go farther away, but can receive enough energy to support life. The presence of two suns can also offer advantages, such as more stable climate over long periods of time, as the stars' gravitational interactions can help keep planets within a stable, predictable path. The atmosphere of a planet in a binary star system will play a crucial role in determining its habitability. Two stars emitting varying levels of radiation. The planet atmosphere will be thick enough to shield the surface from harmful ultraviolet and S-rays, particularly if one or both stars are more active than the sun. At the same time, the atmosphere would need to allow enough light and warmth to reach the surface to support life. On a binary planet, the interaction of two stars creates stunning atmospheric effects. Perhaps a very reward caused by the magnetic field of the two stars will have glow in the light of suns. Mysteries yet to unfold. As we continue to discover more about binary star systems and planets, the potential for life in these worlds remain one of the tantalizing questions of astronomy. Missions like the James Webb Space Telescope and upcoming observatories designed to study exoplanets in detail will be on the cusp of a new era of exploration. These powerful instruments will allow us to probe the atmospheres of binary planets, searching for signs of water vapor, oxygen, and other biosignatures that could hint at the presence of life. Binary star systems, with their dual suns and complex gravitational dynamics, are just one of the many types of planetary systems that challenge our understanding of the universe. They remind us the cosmos is far more diverse and surprising than we ever imagined, with environments that push the boundaries we think is possible. And as we gaze through our telescopes, looking for new worlds, it's entirely possible that the next great discovery in the search for life beyond Earth will come from a planet orbiting two suns, a world where two stars light the sky, and where the story of life is being written in the glow of their combined brilliance. Water-rich planets, ocean beyond Earth, water, the foundation of life as we know it, is not unique to Earth. In the vastness of the cosmos, scientists believe there are entire planets where water is not just present, abundant. These water-rich planets, sometimes referred to as ocean worlds, represent some of the most intriguing destinations in search for life beyond our solar system. Imagine a world where oceans stretch unbroken from horizon to horizon. The land, it exists all, is submerged beneath kilometers of liquid water. These alien oceans, while familiar substance, hold secrets enterprise far beyond our understanding. The suns of water worlds. Water-rich planets are believed to have formed in the colder, outer region of their planetary systems, where water ice was plentiful during the formation of the planet. These worlds may have migrated closer to their stars over time, bringing their vast reservoirs of water with them. Unlike Earth, water covers roughly 7% of Earth, but remains relatively shallow in comparison to the planet's overall size. Water-rich planets may be dominated entirely by deep oceans. Oceans that could be hundreds, even thousands of kilometers deep. In these worlds, water would likely be a fundamental part of planet structure, creating unique layers of ice and liquid, depending on temperature and pressure. Beneath the vast oceans, immense pressure at deep levels will force water into different forms, such as high-pressure ice, which is not the frozen water we know, but a denser, more solid form of ice that can exist even at high temperatures. This layering effect could create entirely alien ocean ecosystems, where life might thrive in environments more extreme than anything found on Earth. Some water-rich planets may even contain an ice mantle, a layer of ice beneath the liquid water, formed by the immense pressure of the overlying ocean. Such a planet could still have active geological processes below this ice mantle, similar to Earth's mantle and core. In these cases, hydrothermal activity could occur where the planet's internal heat causes cracks in the ice, releasing heat and chemicals into the deep oceans above. Such environments similar to Earth's deep-sea hydrothermal vents. Life thrives despite the absence of sunlight. Oceans that cover the world. Imagine standing on the surface of the planets. If you could, the view would be unlike anything you've ever seen. An endless expanse of water stretching out in every direction, with no land sight. The atmosphere might be thick with moisture, constantly feeding the ocean below with rains, or creating immense clouds that hover above, reflecting the light of a distant star. The color of the water could vary depending on the planet's chemistry and the light of its sun, from deep blues to greens, or even darker hues, colored by unknown elements or biological life lurking beneath. These water worlds could have unique weather systems, driven by the interaction between the ocean and atmosphere. Without land to break up weather patterns, massive storms could form, with winds and waves far more intense than anything we see on Earth. On some water planets, superstorms could last for years, driven by constant heat exchange between the ocean and atmosphere, creating monstrous waves and towering clouds that spiral across the surface. Deeper oceans would likely be completely alien environments. On Earth, our deepest oceanic trenches extend about 11 kilometers below surface, but on water-rich planets, these depths could be multiplied many times over. At such depths, life on the surface would be entirely absent, creating a dark, pressurized world where exotic forms of life could evolve. Chemosynthesis, a process where life forms derive energy from chemicals rather than sunlight, could be widespread, just as in Earth's deep-sea vents. The creatures on these planets, if they exist, might be adapted to live in complete darkness under incredible pressure. They could be unlike anything we've ever encountered. Large, slow-moving organisms that glide through deep waters, or entire ecosystems based on floating mats of microbial drifting just below the surface. The possibilities for life on such planets are vast and, as yet, unexplored. The atmospheres of water-rich planets. The atmosphere of a water planet would be an essential factor in determining its habitability. In many cases, water worlds may have dense, thick atmospheres rich in water vapor, creating a greenhouse effect that keeps the surface warm and stable. Even if the planet is the James Telescope and other future missions allow us to study these atmospheres in detail, searching for signatures of water vapor, clouds, and other gases that could indicate the presence of oceans and potentially life. On some water-rich planets, the atmosphere, massive storms could form, with winds and waves far more intense than anything we've seen on Earth. On some water-rich planets, superstorms could last for centuries, driven by constant heat exchange between the ocean and atmosphere, creating monstrous waves and towering clouds that spiral across the surface. The deeper oceans would likely be completely alien environments. On Earth, our deepest ocean trenches extend about 11 miles above the surface. On water-rich planets, these depths can be multiplied many times over. At such depths, life on the surface would be entirely absent, creating a dark, pressurized world where exotic forms of life could evolve. Chemosynthesis, a process where life forms derive energy from chemicals rather than sunlight, could be widespread, just as it is Earth's deep events. The creatures on these planets, if they exist, might be adapted to live in complete darkness and under incredible pressure. They could be unlike anything we've ever encountered. Large, slow-moving organisms that glide through the deep waters, or entire ecosystems become floating with microbial life, drifting just below the surface. The possibilities for life on such planets are vast and as yet unexplored. The atmospheres of water-rich planets. The atmosphere of a water-rich planet would be an essential factor in determining its habitability. In many cases, water worlds may have dense, thick atmospheres rich in water vapor, creating a greenhouse effect that keeps the surface warm and stable, even if the planet is far from its star. The James Webb Space Telescope and other future missions will allow us to study these atmospheres in detail, searching for signatures of water vapor, clouds, and other gases that could indicate the presence of oceans and potentially life. On some water-rich planets, the atmosphere could be in constant flux. The vast surface oceans could contribute to rapid evaporation, creating an atmosphere heavy with moisture. This moisture could condense in a massive cloud system that circle the planet, creating endless rainstorms and contributing to the planet's dynamic weather. In some cases, these atmospheres could be so thick with water that they create a steam world, where the surface is a boiling ocean of water vapor and liquid, surrounded by towering clouds. In more temperate water-rich planets, the atmosphere might resemble Earth's, with a balance of nitrogen, oxygen, and water vapor, probably giving rise to clouds, rain, and even snow. However, the lack of land anchor weather systems could mean the planet is subject to frequent and powerful storms, with winds and waves far stronger than anything seen on Earth. In terms of habitability, the presence of liquid water is a key factor, but the atmosphere also needs to protect the surface from harmful radiation and provide a stable environment for life to thrive. Water-rich planets orbiting and stars, which are known for their intense flares and radiation, would need a thick, protective atmosphere to shield the oceans from bursts of energy. In some cases, the thick atmosphere of water could help regulate temperatures and protect against radiation, allowing life to evolve in the oceans below. Europa, Cetus, and the ice moons, including from our solar system. While exoplanets with vast oceans are a tantalizing prospect, we don't have far from home examples of potential water-rich worlds. Some of the most intriguing for oceans beyond Earth lie within our own solar system. On moons like Europa and Enceladus. Europa, one of Jupiter's largest moons, is covered in a thick shell ice. Beneath that icy, scientists believe there is a global ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. The Europa Clipper mission, set to launch later this decade, aims to investigate Europa's subsurface ocean, searching for clues about its composition and whether its mining ocean would stretch out in all directions, the liquid surface forming the only landscape. Beneath the surface, deep abyss where no sunlight penetrates, life may exist in chemical reactions and internal heat rather than sunlight, just as life rises at Earth's deep-sea hydrothermal vents, where organisms draw from the Earth's internal heat rather than the sun. Life on water worlds might exist in ecosystems. These can be entirely different from anything we've ever seen, yet bound by the same chemistry of life: carbon, water, and energy. Atmospheres and climate, a world of constant change. But these oceans don't exist in isolation. The atmospheres of water worlds play a crucial role in determining the planet's climate and the potential for habitability. A thick atmosphere, rich in water vapor, could envelop the planet, creating a runaway greenhouse effect that traps heat, warming the surface, and potentially bringing the entire planet into a steam world. A place where the surface is not going to an ocean of vapor. These steam worlds may still have ocean beneath their dense atmospheres, but reaching them would require descending through thick cloud steam, where temperatures and pressure. On a temperate water world, the atmosphere might resemble Earth's, with vast amounts of water vapor, nitrogen, and possibly oxygen. These planets could experience dynamic weather systems, constant rainstorms, powerful winds, and enormous cloud formations that swirl across the surface, fed by the endless supply of water. Without land to break up these patterns, storms might grow larger than anything on Earth, superstorms lasting for years, driven by the interaction between the atmosphere and the ocean below. The interaction between the atmosphere and ocean could also be deep circulation patterns, where warm water from the surface sinks into the depths, while cooler water rises in upwelling currents. These movements would influence not just the climate, but potentially the ecosystems within the oceans, providing nutrients and energy to sustain life throughout the water column. A silent, hidden world. The greatest mystery of water worlds lies beneath their waves. What kind of life could exist in a world. Could life on such planets evolve in the same way it did on Earth, where land-dwelling species diversified and adapted? Or would the ocean be the only environment these life forms ever know? In the deep, dark oceans of a water world, sunlight might be a distant memory. If the planet stars, and while that was started, it was only the beginning of what would become a deep, endless exploration of the universe. In time, the window opens wider, and we glimpse Yuri Gagarin, the first human to see Earth from space, to feel the pull of the planet fall away as he soared above the curvature of the globe. The stars beyond him were not just points of light, but destinations, uncharted, waiting for discovery. He carried with him not just the weight of history, but the curiosity of every person on Earth who had ever wondered what lay beyond the atmosphere, beyond the pale blue. And then, as the years unfolded, the window revealed new scenes. The grainy footage of Neil Armstrong and Buzz Aldrin stepping onto the moon, their footprints pressed into the dust of another world. It was a single moment of presence on the moon, but it echoed across time, filling us with wonder and possibility. These human journeys into space weren't just missions. They were first stanzas in a long, unfinished poem about exploration, about seeing beyond the next planet, the next star. Through this window, we see not just the destination we've reached, but the unanswered questions that linger in the night sky. As an astronomer, I often find myself looking beyond visible stars, past familiar places like our moon, or Mars, or the icy moon of Jupiter, the countless exoplanets that are across the way. What stories are waiting to be discovered there? In my mind, those distant worlds, planets or stars so far away we catch the faintest glimmer of spheres, are there somewhere, orbiting a star, a planet might hold water, an atmosphere rich with oxygen, perhaps a faint signature of life. The Kepler Space Telescope. But we're not only looking outward from the window. Space has also taught us to reflect on our place in the universe. Every satellite, every astronaut, every telescope reminds us that it's fragile. That life, this precious, miraculous phenomenon, exists within a delicate balance. Our exploration space has shown us they are connected, not just to stars themselves. And from this window, we can also see the future. Missions that will one day take us further, perhaps to Mars or even beyond. The James Webb Space Telescope, poised to peer deeper into the cosmos than ever before, may soon reveal the atmospheres of distant exoplanets, perhaps even signs of life. It will show us new parts of space history, things we cannot yet imagine, questions we have not yet asked. Space history is not a distant memory, but a living, breathing story, one we are writing with each new discovery, with every question we dare to ask. As I look out from this window, I see not just the stars, but the echoes of the past, the whisper of future journeys, and the certainty that we are only at the beginning of our exploration. The universe is vast, its mysteries boundless, and we, like our ancestors who first gazed up at the sky, are only just beginning to understand our place within it. The stars shine beyond, vast and endless. Yet within that boundless expanse lies the record of our first humble steps toward the infinite. Each of those steps, Sputnik, Gagarin, Apollo, carries with it the pulse of human curiosity, the relentless drive to understand not just where we are, but where we might one day go. That same drive pushes us to peer deeper into the cosmos, now brings us to the precipice of new discoveries. We turn our gaze not just to the stars, but to the worlds orbiting them. Through this window, I think the worlds we've yet to see are not the exoplanets hidden in the light of distant stars, planets we've only begun to detect by watching their stars dim ever so slightly as they pass in front of them. These are the new frontiers of space history, planets that may hold oceans oceans, clouds, and atmospheres filled with the chemical signatures of life. Take the TRAPPIST-1 system, with its 7 rocky planets circling a cool, dim star. From our vantage point, TRAPPIST-1 is just a flicker of light in the constellation Aquarius. But through the lens of our instruments, it becomes known of its star, meaning conditions could potentially allow for liquid water surface. This discovery made Proxima Centauri a prime candidate in the search for a world beyond Earth. Proxima Centauri was discovered by measuring these slight wobbles in the movement of its parent star. The planet has a minimum mass of about 1.17 times that of Earth, classifying as an Earth-like planet or a super-Earth. Its orbital period is about 11.2 days. It completes a full orbit around the star much faster than Earth around the Sun. Despite this close orbit, Proxima Centauri lies within the habitable zone, a region around a star where temperatures could allow for liquid water, a key ingredient for life. Because Proxima Centauri is much cooler and dimmer than the Sun, its habitable zone is a little closer to the star. Proxima Centauri orbits at a distance of about 5 cents, astronomical units, only 5% of the distance between Earth and the Sun. While this might sound perilously close, the reduced luminosity of Proxima Centauri means that the planet receives roughly the same amount of starlight as Earth does from the Sun. A tidally locked world? Most intriguing, yet potentially challenging aspect of Proxima Centauri is the likelihood that it is tidally locked. This means one side of the planet constantly faces the star, while the other side remains in perpetual darkness, much like the moon's relationship with Earth. If Proxima Centauri b is indeed tidally locked, it would have extreme temperature variations between its day side and night side, with one hemisphere receiving continuous sunlight and the other shrouded in eternal darkness. The day side could be blisteringly hot, with direct exposure to Proxima Centauri's radiation, while the night side might be freezing cold. However, in the Terminator Zone, the region between the day and night sides, temperatures might be more moderate, potentially creating habitable conditions. In this twilight region, water might exist, and life could potentially thrive in this narrow band where conditions are more stable. If Proxima Centauri has a thick atmosphere, it can help redistribute heat from the day side to the night side, reducing the temperature extremes. In this scenario, atmospheric circulation plays a crucial role in shaping the planet's climate, allowing for more uniform temperatures across the surface. Oceans, if they exist, could also help moderate the climate by transporting heat, making the planet more hospitable for life. The possibility of an atmosphere, whether or not Proxima Centauri b has an atmosphere, is one of the central questions regarding its potential habitability. A thick atmosphere would not only help moderate the planet's climate, but it could also protect the surface from harmful stellar radiation. However, the stellar flares from Proxima Centauri could have significant consequences for the planet's atmosphere, potentially stripping it away over time. Stellar flares emit high-energy particles and radiation that could erode a planet's atmosphere, particularly on planets orbiting close to their star, like Proxima Centauri b. Without a strong magnetic field or a protective atmosphere, Proxima Centauri be exposed to harmful radiation, needed for life survival. Despite these challenges, some suggest Proxima Centauri b might have retained its atmosphere, possibly due to a strong magnetic field or other factors. If the planet does have an atmosphere, it would be key to understanding its potential habitability. Future missions and telescopes, such as the James Webb Space Telescope, may be able to study atmospheric composition of Proxima Centauri b, providing critical data about its environment, Proxima Centauri's flares, and their impact. One of the major hurdles to life on Proxima Centauri b is the intense stellar activity of its parent star. Proxima Centauri, like many red dwarfs, regularly emits stellar flares, bursts of radiation that can dramatically increase the amount of ultraviolet and X-ray radiation hitting the planet. These flares can strip away the atmosphere and damage any potential biosphere. A 2017 observation captured one of the largest flares ever seen from Proxima Centauri, which temporarily increased the star's brightness by a factor of 1,000. Such flares, if frequent, could be devastating to a planet like Proxima Centauri b. However, some scientists believe that if the planet has a sufficiently thick atmosphere or a strong magnetic field, it still retains habitability in some regions. One possibility is that life on Proxima Centauri b, if it could have adapted to these flares. Life forms might evolve to thrive underground or beneath oceans, where it would be shielded from the most harmful radiation. Alternatively, life could exist in the shadow side planet, protected from the intense radiation of a flaring star. Potential habitability and the search for life. Despite challenges posed by proximity to a flare star and potential tidal, Proxima Centauri remains one of those prime candidates for habitability outside our solar system. If liquid water exists on the surface and the planet has retained its atmosphere, Proxima Centauri could give life, possibly environments similar to the deep ocean ecosystems on Earth. The potential for life in the twilight zone, where temperatures are more stable, is one of the most exciting aspects of planet discovery. In such a scenario, the interplay between light and dark could create complex ecosystems that are shaped by the unique environment of a tidally locked world. Even if life does not exist on the surface, it is possible that real life could survive in subsurface environments, protected from harsh conditions above. In the coming years, astronomers hope to study Proxima Centauri b in detail, Instruments like James Webb Telescope and ground observatories will allow scientists to analyze the light from Proxima Centauri B as it passes through the planet's atmosphere, searching for signs of vapor, oxygen, and other gases that could indicate habitability. Breakthrough Starshot, an ambitious project backed by physicist Stephen Hawking and billionaire Yuri Milner, aims to send small, light-powered spacecraft to the Alpha Centauri system in the next few decades. These probes, if successful, provide direct imaging and data on Proxima Centauri B, offering an unprecedented glimpse into this near world. A vision of Proxima Centauri B. What might Proxima Centauri look like? Imagine standing in the twilight zone, with one side of the sky glowing with a faint light of a red dwarf star, while the other side fades in the deep, endless night. The atmosphere, if present, might be thick with clouds, and strong wind could sweep across the surface. The heat from the day side is carried to the night side. In the distance, towering storms could form on the day side, where the constant heat drives powerful weather patterns. Oceans, if they exist, might be churning near the pole of the planet's tidal forces, with waves crashing into rocky shores in the twilight. On the night side, the temperature drops rapidly, freezing the oceans and creating vast expanses of ice. Beneath the surface, in the depths of the ocean or within the planet's crust, life can thrive, adapted to survive in extreme conditions, shielded from the radiation above. Microbial life, similar to the extreme files that survive in Earth's harshest environments, would be the dominant form of life here, clinging to the narrow regions where conditions are just right for survival. The future of exploration. Proxima Centauri is not just a curiosity, it's a target. Its proximity to Earth means that it's one of the few exoplanets we may be able to study in detail within our lifetimes. Future missions to the Alpha Centauri system, combined with next-generation telescopes, may allow us to determine once and for all whether this planet is habitable or even inhabited. Could we one day walk there, feel the faint warmth of a different star on our skin, and look to see unfamiliar constellations? And then Kepler 452b, a world has been called Earth's cousin, orbiting in the habitable zone of a star much like our sun. Kepler 452b might be covered green, its landscape lush and fertile, with clouds drifting lazily of a landscape of towering mountains and deep valleys. There perhaps, all as it does here, nourishing life that grows involves untouched human hands, but to us by the same cosmic forces that shaped our own Earth. One of the worlds that circled distant stars like LHS 1140b, a rocky planet just 40 light years away. Gravity would be stronger, the air heavier, atmosphere rich in possibilities. Perhaps dense clouds swirling across a cobalt horizon, with winds carrying the scent of alien oceans. Thick we have to imagine. The light there might be faint, a soft glow from the red dwarf star, casting the landscape in perpetual twilight, a world forever on the cusp of dawn or dusk. In the TRAPPIST, one system, 7 rocky worlds orbit a cool, dim star, each unique and beautiful in its own right. Imagine standing on one of those planets, with the other 6 hanging low in the sky like moons. The sunsets that might be like nothing we've ever seen. Deep purple skies, faded amber, with bands of starlight filtering through the thin atmosphere. What life could thrive in such a place, under the gentle glow of an ultra-cool star, where days stretch long and the warmth is ever so faint. Beyond star we know, there are surely worlds that defy all expectations. Planets where seas of methane glisten under emerald skies, where clouds of ammonia rise high above mountains. There could be gas giants with moons as beautiful and varied as the planets themselves, some covered in tropic storm that rage for centuries. Others with clear oceans that reflect the stars though they were mirrors. It might be water worlds, entire planets covered in oceans, with endless waves stretching from horizon to horizon, warmed by a distant sun and teeming with life in its depths. One can only dream of the beauty of a world like Gliese 581g, an exoplanet that orbits a star in a habitable zone, where the temperature is just right for liquid water. Perhaps this world is cloaked in mists, its surface obscured from our distant gaze, a life flourishes under the watchful eye of a red sun. Trees with leaves dark as night might stretch toward the sky, gathering every last photon of light, while rivers of crystal-clear water carve paths through fertile plains, home to creatures as varied and one planet exists, but that more detailed observations are needed for presence. The Gliese 581 system remains a prime target for their study, as other planets in the system, including Gliese 581, also lie near the habitable zone, making one of the most promising nearby star systems in the search for habitable worlds. The future of Gliese 581G exploration. Gliese 581G's status remains uncertain. It highlights the challenges and excitement of discovering potentially habitable exoplanets. Future telescopes, such as the James Webb Space Telescope, are expected to bring us much closer to understanding distant worlds like Gliese 581G. These instruments will be able to analyze the light passing through exoplanet atmospheres, providing detailed information about their composition and structure. In the case of Gliese 581G, one of the most important steps would be to confirm its existence and then focus on determining whether it has an atmosphere. If we find that it does, the next step would be to search for a sign of habitability, such as the presence of water vapor or other biosignatures. Even if Gliese 581G proves not to exist, the search for Earth-like exoplanets in a habitable zone of nearby stars will continue. Red dwarfs like Gliese 581 are prime targets because their small size and cooler temperatures make it easier to detect planets orbiting close by. The discovery of Gliese 581G has already shifted the focus of exoplanet research toward these small stars, where the potential for a habitable world might be greater than we ever imagined. A vision of Gliese 581G. If Gliese 581G does exist, what might it look like? Imagine standing on the surface of a highly light planet, one side forever bathed in light and the other shrouded in eternal darkness. In the twilight zone, the sky glows with a pale orange or red hue, reflecting the soft, dim light of its red dwarf star. The landscape might be rocky and barren in places, but along the edge of the light, liquid water could flow in rivers and seas. The air is dense with moisture, swirling patterns that balance the extreme temperatures between the two sides of the planet. If you look toward the bright horizon, you might see storm clouds gathering, heat from the star drives intense weather systems. Behind you, the sky fades into deep darkness, where the stars glimmer coldly over a frozen landscape. Life exists in lands. The balance of light, water, and temperature creates just the right conditions for survival. In search for life beyond Earth, Gliese 581G remains one of the most fascinating and enigmatic possibilities. Whether it proves to be a planet or just a fossil, discovery opened our eyes to the potential of the universe, showing that the ingredients for life could be scattered across the cosmos, leaving for us to find them. And what about the mysterious watch planets that might exist in abundance? Imagine a planet where entire continents float on vast, deep oceans. Their surface is dotted with archipelagos of glowing bioluminescent life. Beneath waves, ancient creatures swim through the depths. Their movement is slow and graceful, as the oceans themselves breathe in time with tides their distance are. The skies above these water worlds might shimmer for us, caused by magnetic fields more powerful than anything known on Earth, creating dazzling displays of light as particles from their parent stars interact with the planet's atmospheres. Perhaps the most beautiful worlds are those that challenge our understanding of what life is. Planets that orbit binary stars, where two suns cast overlapping shadows, creating twilight zones where they find friction, delicate balance of light and dark. The landscapes of these worlds could be otherworldly, sand dunes stretching out under two suns, with deep canyons carved by the winds that howl through them. Or perhaps the surface is dotted with glass lakes that reflect both stars. The surface is rippling in the wind like pools of liquid light. As we look from this window, we're filled with a sense of awe and possibility. The universe is not a cold, empty place, but a canvas filled with vibrant worlds, each one with its own unique beauty and its own story to tell. The light from these distant planets has traveled for thousands, millions, even billions of years to reach us. And as we study that light, we begin to understand that the beauty of the universe is far more complex and diverse than we ever imagined. Each of these worlds, seen or unseen, represents a new chapter in the story of space exploration, a chapter that humanity has only just begun to write. We ascend our robotic explorers to the edges of our own solar system. But the real journey is just beginning. With each new telescope, each new mission, we are opening windows into new worlds, revealing the wonder of the universe one planet at a time. These beautiful worlds, with failing skies, unfamiliar landscapes, and untold secrets, are waiting for us. They're out there, just beyond our reach, but closer than ever before. Through the light we capture, through the mission we send, and through the dreams we pursue, we're getting closer to standing not just the universe, our place in it. And one day, perhaps, we will stand one of those beautiful worlds, looking up at a new sky, knowing that from a window long ago, we first caught a glimpse of the vastness and beauty that awaited us. In the tapestry of the cosmos, there are few phenomena as captivating and mysterious as binary stars, pairs of stars bound together by gravity, orbiting a common center of mass. These celestial duos are not rare. In fact, nearly half of all stars in the universe are part of binary or multiple star systems. But it is their dynamic, complex relationships that make them so fascinating. As we peer through the window of space exploration, we catch glimpses of these systems and the planets that might orbit within them, revealing a universe far more intricate than we once imagined. A cosmic dance of light and gravity. At first glance, binary stars may appear similar to this we're familiar with, like our own Sunday. But these pairs of stars are locked in a delicate dance, their gravitational pulls keeping them in constant motion around one another. This movement creates a cosmic ballet, where the stars orbit a common center where conditions might allow liquid water to exist on the surface. In such systems, the changing light from two suns could lead to fascinating variations in climate and weather, potentially giving rise to life forms adapted to fluctuating conditions. Planets orbiting just one of the stars in a binary system might also experience periods of enhanced energy as the second star approaches, potentially boosting photosynthesis and other biological processes. Life on such worlds could evolve to take advantage of these cycles, thriving during the times when both stars' light reaches the planet's surface and entering periods of dormancy or reduced activity when one star seeds. However, binary star systems also present challenges. The complex gravitational dynamic can make planetary orbits less stable, and the intense radiation of certain stars, such as red giants or massive blue stars, could pose significant hurdles for life. The discovery of planet like Kepler-47c, a gas giant orbiting a binary star, suggests planet formation is possible in these systems, and there are planets with for life remains. The next frontier, exploring binary systems. As we peer deeper into the universe, the study of binary stars will continue to play a crucial role in our understanding of star formation and the search for habitable worlds. With the advent of advanced telescopes like the James Webb Space Telescope, we are poised to explore these systems in even greater detail. JWST will allow us to observe the atmospheres of exoplanets orbiting binary stars, helping us whether these distant worlds could support life. Future missions can also send probes to the Alpha Centauri system, the closest binary star system to Earth, located just over 4 light-years away. Alpha Centauri consists of two stars, Alpha Centauri A and Alpha Centauri B. The possibility of a third star, Proxima Centauri, which has its own planet Proxima b. These stars offer a tantalizing opportunity to study a binary system up close and to explore the potential for habitable planets in cosmic regard. As we gaze through the window in the night sky, we realize stars are not just astronomical curiosities. They are dynamic systems filled with potential for discovery. Whether through the drama of stellar collisions, the gentle dance of two suns, or the prospect of life under a dual star system, binary stars remind us that or rapidly changing cloud formations. Some circumlunar planets might experience binary eclipses, where one star passes in front of the other. This could lead to brief periods where the planet is shaded from the light of one of its suns, creating a temporary cooling effect similar to an eclipse on Earth, but potentially lasting longer or affecting the entire planet. Such events could have a dramatic effect on the planet's ecosystem and climate, causing rapid shifts in temperature and light levels. The habitability of planets with two suns. One of the most exciting prospects in study of binary star systems is the potential for habitable planets, worlds with conditions, liquid water, and life. While binary star systems were once thought to be unlikely hosts for life, the discovery of circumlunar planets like Kepler-16b and others has shown that these systems can indeed support stable planetary orbits. The question now is whether any of these planets could be located in a habitable zone, the region where temperatures are just right for liquid water to exist. In a binary system where both stars are relatively small and cool, such as two dwarfs or a dwarf and a K-dwarf, the habitable zone could be clear of the stars. In these systems, a planet in the habitable zone might experience mild temperatures, with combined light from the two stars providing enough warmth for good water without overwhelming the planet with radiation. Conversely, in systems where one or both stars are hotter and more massive than the sun, the habitable zone would be farther out. The combined heat and radiation of the two stars would be more balanced. These planets may orbit far away, but still receive enough energy to support life. The presence of two suns could also offer some advantages, such as a more stable climate over long periods of time, as the stars' gravitational interactions could help keep the planet orbit in a stable, predictable path. The atmosphere of a planet in a binary star system would play a crucial role in determining its habitability. With two stars emitting varying levels of radiation, the planet's atmosphere would need thick enough to shield the surface from harmful ultraviolet and X-rays, particularly if both stars are more active than our sun. At the same time, the atmosphere would need to allow enough light and warmth to reach the surface to support life. On a binary planet, the interaction of two stars could create stunning atmospheric effects, perhaps vibrant auroras caused by magnetic fields of the two stars, or clouds that glow in the light of both suns. Mysteries yet to unfold. As we continue to discover more about binary star systems and their planets, the potential for life in these worlds remains one of the most tantalizing questions in astronomy. With missions like James Webb Space Telescope and upcoming research designed to study exoplanet in detail, we are on the cusp of a new era of exploration. These powerful instruments will allow us to probe the atmospheres of circumlunar planets, searching for signs of water vapor, oxygen, and other biosignatures that hint at the presence of life. Binary star systems, with their dual suns and complex gravitational dynamics, are just one of the many types of planetary systems that challenge our understanding understanding of the universe. They remind us that the cosmos is far more diverse than we ever imagined, with environments that push the boundaries of what we think is possible. And as we gaze through our telescopes, looking for new worlds, it's entirely possible that the next great discovery in the search for life beyond Earth could come with no land in sight. The atmosphere might be thick with moisture, constantly feeding the ocean below with rains or creating immense clouds that hover above of a distant star. Water could vary depending on the planet's chemistry and from deep greens or ooze, colored by unknown elements or by alien environments. Our east oceanic trenches extend about 11 kilometers below the surface, but on water-rich planets, these depths could be multiplied many times over. At such depths, life from the surface would be entirely absent, creating a dark, pressurized world where exotic forms of life could evolve. Chemosynthesis, a process where life forms derive energy from chemical sunlight, could be widespread, just as Earth's events. The creatures on these planets, if they exist, might be adapted to live in complete darkness and under incredible pressure. They could be unlike anything we've ever encountered. Large, slow-moving organisms live in deep waters, or entire ecosystems based on fleeting mass microbial life drifting just below the surface. The possibilities for life on such planets are vast and yet unexplored. The atmospheres of water planets. The atmosphere of a water planet will be an essential factor in determining its habitability. In many cases, water worlds may have dense, thick atmospheres of water vapor, creating a greenhouse effect that keeps surface warm and stable, even if the planet is far from the star. The James Webb Space Telescope and Mission will allow us to study these atmospheres in detail, searching for signatures of water vapor, clouds, and other gases that could indicate the presence of oceans and potentially life. On some water-rich planets, the atmosphere being constant flux. The vast oceans contribute to rapid evaporation, creating an atmosphere heavy with moisture. This moisture could condense into massive cloud systems that circle the planet, creating endless rainstorms and contributing to the planet's weather. In some cases, these atmospheres be so thick with water vapor that create a steam world, where the surface is a boiling ocean of water vapor and liquid, surrounded by towering clouds. In more water-rich planets, the atmosphere might resemble Earth's, with the balance of nitrogen, oxygen, and water vapor, possibly rise to clouds, rain, even snow. However, the lack of land to anchor weather systems could mean the entire planet is subject to frequent powerful storms, with winds and waves far stronger than anything seen on Earth. In terms of habitability, the presence of good water is a key factor, but the atmosphere also needs to protect the surface from harmful radiation and provide a stable environment for life to thrive. Water-rich planets orbiting dwarf stars, which are known for their intense flare and radiation, would need a thick protective atmosphere to shield the oceans from these bursts of energy. In some cases, the thick atmosphere of a water world could help regulate temperatures and protect against such radiation, allowing life to evolve in the oceans below. Europa, Enceladus, and the ice moons, clues from our own solar system. While exoplanets with vast oceans are a tantalizing prospect, we don't have to look far from home to find examples of potential water-rich worlds. Some of the most intriguing candidates for oceans beyond Earth lie within our own solar system, on moons like Europa and Enceladus. Europa, one of Jupiter's largest moons, is covered in a thick shell of ice. Beneath that icy crust, scientists believe there is a global ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. The Europa Clear mission, set to launch later this decade, aims to investigate Europa's subsurface ocean, searching for clues about its composition and whether it might harbor life. If Europa's ocean contained hydrothermal vents or other sources of chemical energy, it could be a prime location for terrestrial life, living in dark, cold waters beneath the ice. Similarly, Enceladus, a small moon of Saturn, has captivated scientists since the discovery of waterized plumes shooting from its south pole. These plumes, which contain organic compounds, are thought to originate from subsurface ocean beneath the moon's icy crust. The heat required to keep the ocean from freezing likely comes from geological activity, similar to what we see in Earth's oceans near hydrothermal vents. These plumes have been sampled by the Cassini spacecraft, and findings suggest that Enceladus could be another potential home for life. While these moons are much smaller than the planets we imagine, they offer a critical clue about how water-rich worlds might form and behave. Studying Europa, Enceladus, and ocean moons gives us a blueprint for understanding how deep oceans can exist in environments far from the north of the sun, and how life might thrive in such extreme conditions. Super-Earths and sub-Neptunes, likely water-rich planets. Many of the exoplanets discovered by the Kepler Space Telescope and other missions fall into a category known as super-Earths or sub-Neptunes, planets larger than Earth, smaller than Neptune. These planets are thought to be some of the most likely candidates for water-rich worlds. Their size and density suggest they may have large amounts of water, potentially covering surfaces or existing as thick layers beneath the atmosphere. For example, the exoplanet Kepler 22b, located in the habitable zone of its star, is believed to be a super-Earth with a significant amount of water. It could be a water-rich world with deep oceans, or even a surface hiding in beneath. Similarly, GJ1214b, a sub-Neptune just 40 light years from Earth, has been studied extensively for signs of water. While its atmosphere remains mysterious, scientists believe its density suggests a water-rich interior, possible with thick atmosphere seen. These super-Earths and sub-Neptunes represent some of the promising candidates for finding water-rich worlds outside our solar system. As we continue to study their atmosphere and surfaces with new technology, we soon discover signs of water, and possibly life, on these planets. The search for life on water-rich planets. Water is the key ingredient for life as we know it, and finding it on distant worlds is one of the most promising signs that these planets might harbor life. While Earth is the only known planet where life exists, the discovery of water-rich planets opens up the possibility that life could evolve in environments very different from our own. On water worlds, life might take on forms that we can scarcely imagine. Instead of land-based ecosystems, entire biospheres could exist in the oceans, from surface-dwelling microorganisms to deep-sea creatures that thrive near hydrothermal vents. These planets might lack the familiar structures of mountains and forests. Water-rich planets, oceans beyond Earth. Water, the foundation of life as we know it, is not unique to Earth. In the vastness of the cosmos, scientists believe there are entire planets where water is not just present, but abundant. These water-rich planets, sometimes referred to as ocean worlds, represent some of the most intriguing destinations in the search for life beyond our solar system. Imagine worlds where oceans stretch unbroken from horizon to horizon, where land, if it exists at all, is submerged beneath kilometers of good water. These oceans, while familiar in substance, could hold secrets and surprises far beyond our understanding. The science of water worlds. Water-rich planets are believed to have formed in colder, outer regions of their planetary systems. Water ice was plentiful during the formation of the planet. These worlds may have migrated closer to their stars over time, bringing vast reservoirs of water with them. Unlike Earth, water covers roughly 70% of the surface, but remains relatively shallow in comparison to planets of all size. Water planets may be dominated entirely by deep oceans. Oceans that can be hundreds, thousands of kilometers deep. In these worlds, water would likely be a fundamental part of the planet's structure, creating unique layers of ice and liquid depending on the temperature and pressure. Beneath the vast surface oceans, immense pressures at deeper levels will force water to different forms, such as high-pressure ice, which is not the frozen water we know, but denser, more solid form of ice that exists even at high temperatures. This layer, in effect, create entirely alien ocean ecosystems, where life might thrive in environments more extreme than anything found on Earth. Some water planets may even contain an ice mantle, a layer of ice beneath the liquid water, formed by immense pressure of the overlying ocean. Such a planet could still active geological processes below this ice mantle, similar to Earth's mantle core. In these cases, hydrothermal activity could occur when the planet's internal heat causes cracking ice, releasing heat and chemicals into the deep oceans above. Such environments would be similar to Earth's deep-sea hydrothermal vents, where life thrives despite the absence of sunlight. Oceans that cover the world. Imagine seeing the surface of one of these planets if you could. The view would be unlike anything you've ever seen. An endless band of water stretching out in every direction, with no end in sight. The atmosphere may be thick with moisture, constantly heating the ocean below with rains, or creating mid clouds that hover above, feeding the light of the star. The color of water could vary depending on plant's chemistry and the light of the sun. deep blues to greens or even darker hues, colored by unknown elements or biological life lurking beneath. These water worlds could have unique weather systems, driven by the interaction between ocean and atmosphere. That land break up weather patterns, massive storms form, with winds and waves far more intense than anything we see on Earth. On some water-rich planets, superstorms last for centuries, driven by constant heat exchange between the ocean and atmosphere, creating monstrous waves and towering clouds that spiral across the surface. Deeper oceans would likely be completely alien environments. On Earth, our deepest oceanic trenches extend about 11 kilometers below the surface, but on water-rich planets, these depths could be multiplied many times over. At such depths, life surface would be entirely absent, creating a dark, pressurized world where exotic form of life could evolve. Chemosynthesis, a process where life forms derive energy from chemicals rather than sunlight, could be widespread, just as it is at Earth's deep sea vents. The creatures on these planets, if they exist, might be adapted to live in complete darkness and under incredible pressure. They could be unlike anything we ever encountered. Large, slow-moving organisms that glide through the deep waters, or entire ecosystems based on floating mats of microbial life drifting just below the surface. The possibilities for life on such planets are vast and as yet unexplored. The atmosphere of water-rich planets. The atmosphere of a water-rich planet would be an essential factor in determining its habitability. In many cases, water worlds have dense, thick atmospheres rich in water vapor, creating a greenhouse effect that keeps the surface warm and stable, even if the planet is far from a star. The James Webb Space Telescope and other future missions will allow us to study these atmospheres in detail, searching for signatures of water vapor, clouds, and other gases that can indicate the presence of oceans in life. On some water-rich planets, the atmosphere could be in constant flux. The vast surface ocean contributes to rapid evaporation, creating an atmosphere heavy with moisture. This moisture could condense into massive cloud systems that circle the planet, creating endless rainstorms and contributing to the planet's dynamic weather. In some cases, these atmospheres could be so thick with water vapor that they create a steam world. The surface is a boiling ocean of water vapor and liquid, surrounded by clouds. In more temperate water-rich planets, the atmosphere might resemble Earth's, with a balance of nitrogen, oxygen, and water vapor, possibly giving rise to clouds, rain, and even snow. However, the lack of land-to-anchor weather systems could mean that the entire planet is subject to frequent and powerful storms, with winds and waves far stronger than anything seen on Earth. In terms of habitability, presence of water is a key factor. But the atmosphere also needs to protect the surface from harmful radiation and provide a stable environment for life to thrive. Water-rich planets orbiting and dwarf stars, which known for their intense layers and radiation, would need a thick, protective atmosphere to shield the oceans from the bursts of energy. In some cases, the thick atmosphere of the water world can help regulate temperatures and protect against saturation, allowing life to evolve in the oceans below. Europa, Enceladus, and the ice moons, clues from our own solar system. While exoplanets with vast oceans are a tantalizing prospect, we don't have to look far from home to find examples of potential water-rich worlds. Some of the most intriguing candidates for oceans beyond Earth lie within our own solar system, on moons like Europa and Enceladus. Europa, one of Jupiter's largest moons, is covered in a thick shell of ice. Beneath that icy crust, scientists believe is a global ocean of liquid water, kept warm by tidal forces from Jupiter's gravity. The Europa mission, set to launch later this decade, aims to investigate Europa's subsurface ocean, searching for clues about its composition and whether it might harbor life. If Europa's oceans contain hydrothermal vents or other sources of chemical energy, it could be a prime location for extraterrestrial life, leaving the dark, cold waters beneath the ice. Similarly, Enceladus, a small moon of Saturn, has captivated scientists since the discovery of waterized plumes shooting from its saddle. These plumes, which contain organic compounds, are thought to originate from the surface ocean beneath the moon's icy crust. The heat required to keep this ocean free likely comes from geological activity, similar to what we see in Earth's oceans near hydrothermal vents. These ones have been sampled by the Cassini spacecraft, and the findings suggest that Enceladus could be another potential home for life. While these moons are much smaller than the exoplanets we imagine, they offer critical clues about how water-rich worlds might form and behave. Studying Europa, Enceladus, and other ocean moons gives us a blueprint for understanding how deep oceans can exist in environments far from the warmth of the sun and how life might thrive in extreme conditions. Super-Earths and sub-Neptunes, likely water-rich planets. Many of the exoplanets discovered by the Kepler Space Telescope and other missions fall into a category known as super-Earths or sub-Neptunes, planets larger than Earth but smaller than Neptune. These planets are thought to be some of the most likely candidates for water worlds. Their size and density suggests they may have large amounts of water, potentially covering the surface or existing in thick layers beneath the atmosphere. For example, the exoplanet Kepler 22b, located in a habitable zone star, is believed to be a super-Earth with a significant amount of water. It could be a water-rich world with deep oceans, or an ice-covered surface hiding the ocean beneath. Similarly, GJ1214b, a sub-Neptune 40 light-years from Earth, is studied extensively for signs of water. While its atmosphere remains mysterious, scientists believe that its density suggests a water-rich interior, possibly a thick atmosphere of steam. These super-Earths and sub-Neptunes represent some of the most promising candidates for fitting worlds outside our solar system. As we continue to study their atmospheres and surfaces with new technology, we may soon discover signs of water and possibly life on these distant planets. The search for life on water-rich planets. Water is a key ingredient for life as we know it, and finding it on this world is the most promising sign that the planets need hard life. Earth is the only known planet that exists. The discovery of water-rich planets opens up the possibility that life could evolve in environments very different from our own. In water worlds, life might take on forms that we can scarcely imagine. Instead of land-based ecosystems, entire biospheres could exist in the oceans, from surface to microorganisms, deep-sea creatures that thrive near hydrothermal vents. These planets might lack the familiar structures of mountains and forests. A water world. We stand on the edge of discovery, looking out into the cosmos and asking one of the most fundamental questions: what else might life exist? Water, the key ingredient for life as we know it, isn't confined to Earth. It's out there, scattered across the universe, forming the oceans of distant alien worlds. These water-rich planets, all known as water worlds, invite us to imagine life far from the shores of Earth, in places where water doesn't fill oceans and lakes. It dominates the entire planet. A water world is a place where liquid water covers nearly the entire surface, or perhaps lies just beneath the flare ice. These planets form regions of space rich in water ice. And over time, through planetary migration or gravitational interactions, they find themselves closer to their stars, where the ice melts into vast, deep oceans. It's a process that began in our own solar system, the icy moons of Jupiter and Saturn, and against the exoplanets we now just beginning to discover. Oceans deeper than imagination. On Earth, the ocean's deepest point, the Mariana Trench, plunges nearly 11 kilometers below the surface. Yet on a water world, oceans might extend hundreds, even thousands of kilometers deep. Imagine a planet where water doesn't stop at shallow depths, but continues downward through layers on layers of liquid, until the pressure becomes so great that the water itself changes form. These immense pressures, water is what we call hot pressurized phases. It's counterintuitive. Ice formed an environment of immense heat and pressure. But under these extreme conditions, water solidifies forms that we don't see on Earth, creating new types of ice that are more dense than the liquid above. This layering, liquid water on top, high pressure ice below, can shape the entire geology of the water world. On Earth, tectonic plates move over the molten mantle, creating dynamic geology we are familiar with. But on the water world, these tectonic plates might instead glide over a layer of ice, with no land mass breaking through the surface to form continents or islands. Instead, an endless world span will stretch out in all directions, the liquid surface forming the only landscape. Beneath the surface, deep in the abyss where no sunlight penetrates, life made is divided shaped by chemical reactions and internal heat rather than sunlight. Just as life thrives Earth's deep-sea hydrothermal vents, where organisms draw energy from the Earth's internal heat rather than sun, and water worlds might exist in deep, hidden ecosystems. These can be entirely different from anything we've ever seen, yet bound by the same history of life: carbon, water, and energy, atmospheres, and climate, a world of constant change. But these oceans don't exist in isolation. The atmospheres of water worlds play a crucial role in turning the planet's climate and potential habitability. A thick atmosphere, rich in water vapor, picks up the planet, creating a runaway greenhouse that traps heat, warming the surface, and potentially turning the entire planet into a steam world, a place where the surface is not liquid water, but an ocean of vapor. These steam worlds may still have oceans beneath their dense atmospheres, but reaching them requires descending through thick clouds of steam, temperatures, pressure. On a more tepid water world, the atmosphere might resemble Earth's, balanced amounts of water vapor, nitrogen, possibly oxygen. These planets could experience dynamic weather systems, constant rainstorms, powerful winds, and enormous cloud formation that swirl across the surface, fed by an endless supply of water. Without land to break up these patterns, storms might grow larger than any we've seen on Earth, superstorms lasting for years, drive the interactions between the atmosphere and the ocean below. The interaction between the atmosphere and ocean can also create deep circulation patterns, where warm water on the surface sinks into this, while cooler water rises in upwelling currents. These movements would influence not just the climate, but potentially the ecosystem within the oceans, providing nutrients and energy to sustain life throughout the world. Silent, hidden world. The greatest mystery of water world lies beneath their waves. What kind of life could exist in a world without land? Could life on such planets evolve in the same way it did on Earth, where land-dwelling species diversified and adapted? Would the ocean be the only environment these life forms ever know? In the deep, dark oceans of the water world, sunlight might be a distant memory. If the planet is far from its star, or if the atmosphere is too thick, no light would reach the depths. Life in these oceans would need to rely on chemosynthesis, a process where energy is derived from chemical reactions rather than sunlight. On Earth, chemosynthetic bacteria thrive near hydrothermal vents, drawing energy from the chemical compounds emitted by the planet's internal heat. On the water world, life might evolve to take advantage of similar processes, existing isolated pockets near sources of geothermal activity. Heat and chemicals rising from the planet's core, warming the deep ocean and providing raw materials for life. But these environments could also have their own challenges. The lack of sunlight means photosynthesis, one of the fundamental processes for life on Earth, would not be possible, and life might evolve in ways that we can't yet predict. Complex ecosystems could exist in the hidden depths, entirely separate from the surface world. With interplay of heat, chemicals, and pressure creates unique conditions for survival. This is for water worlds. With missions like James Webb Space Telescope, we are now closer than ever to finding these water worlds. Through careful observation of distant stars, we can detect planets that fall within the habitable zone, the region around a star where conditions are right for liquid water to exist. We can analyze the light from these planets as it passes through their atmospheres, searching signs of water vapor, clouds, or other gases that might hint at the presence of oceans. In our own solar system, the icy moons of Europa and Enceladus are hidden oceans beneath thick layers of ice, offer tantalizing clue about what water worlds might look like. These moons may harbor liquid oceans, warmed by the internal heat of their planets, and scientists eagerly awaiting the result of upcoming missions like Europa, which will explore its icy moon in detail. But the search for water-rich exoplanets takes us even farther from home. Planets like Kepler, K2b, or GJ-1214b are on candidates for water worlds, super Earths or oceans with thick atmospheres and low densities, suggesting the presence of vast amount of water. These planets are located in habitable zones of their stars, meaning that water could exist on their surface. If they're indeed water worlds, they may hold the key to understanding how common life is in the universe, and what form that life might take. Life beneath waves. As we continue our search for life beyond Earth, water worlds represent one of the most promising environments to explore. With vast oceans, complex climates, unique geological processes, these planets harbor life in forms that are completely alien to us. Life on a water world might never know land, but it thrives in the darkness and pressure of the oceans, in ways we can only begin to imagine. Through the study of water worlds, we're expanding our understanding of what life can be, how it might adapt, evolve, and survive in environments far different from our own. In the depths of these oceans, we may one day find the answers to one of humanity's greatest questions. Are we alone? Or is life thriving in the uncharted waters of distant worlds, waiting for us to discover it? Water worlds are not a possibility. They're likely abundant in the universe. And as we gaze out at the stars, we are reminded that the cosmos holds more than we could ever dream. Somewhere out there, entire planets are covered in oceans, silently waiting for us to find them. Through this window, we glimpse the infinite possibilities of the universe, distant stars, mysterious exoplanets, and the enduring questions of whether life might exist somewhere there. Each new discovery brings us closer to understanding our place in the cosmos. Reminding us that space exploration is not just about the stars, but about unlocking secrets of life, existence, and the future. As we continue to peer into the vast unknown, every mission, every telescope, and every planet brings us closer to those answers. So, join us as we journey through the cosmos, uncovering the mysteries that lie beyond. If you enjoy this journey through space and want to stay updated on latest space exploration, subscribe to our channel and hit the notification bell so you never miss a video. There's a whole universe out there waiting to explore. We want to be part of it. Thanks for watching. Being out, we're no longer bound or flown. Our planet drifts quietly beneath us, a cradle of life suspended in vastness. But beyond it, just past the window, the story of space unfolds. Not just in moment of triumph, but in whispered distant worlds and the secret they hold. There, in the darkness, we can trace the outline of Sputnik, humanity's first tentative step into the cosmic sea. It was more than just a satellite. It was the beginning of an idea. The idea that our future, our destiny, was out there, somewhere in stars. And while that was the start, it was only the beginning of what would come deep, endless exploration of the universe. Time, the window opens. We glimpse Yuri Gagarin, the first human to see from space, to feel the pull of the planet fall away and soar above the curvature of the globe. The stars beyond him were not just points of light, but destinations. Uncharted, waiting for discovery. He carried with him not just the weight of history, but the curiosity of every person on Earth who had ever wondered what lay beyond the atmosphere, beyond pale blue. And then, as the years unfolded, the window revealed new scenes. The grainy footage of Neil Armstrong, Buzz Aldrin staggering onto the moon. Their footprints pressed into the dust of the world. It was a single moment of Prince of the Moon. It echoed across time, filling us with wonder and possibility. These human journeys in space weren't just missions. They were first stanzas in a long, unfinished poem about exploration, about seeing what was beyond the next horizon, the next planet, the next star. Through this window, we see not just the destinations we've reached, but the unanswered questions that linger in the night sky. As an astronomer, I often find myself looking beyond the visible stars, past familiar places like our moon or Mars, or the icy moon of Jupiter, to the countless exoplanets scattered across the Milky Way. What stories are waiting to be discovered there? In my mind, those distant worlds, planets orbiting stars so far away we can only catch the faintest glimpse of their atmospheres, are the somewhere orbiting a distant star, a planet might hold liquid water, an atmosphere rich with oxygen, or perhaps the faint signature of life. The Kepler Space Telescope. We're not only looking outward from this window. Space history has also taught us to reflect on our place in the universe. Every satellite, every astronaut, every telescope reminds us that Earth is fragile, that life, this precious miraculous phenomenon, exists in a delicate balance. Our exploration of space has shown us that we are connected, not just to each other, but to the stars themselves. From this window, we can also see the future. Missions that will one day take us further, perhaps to Mars or even beyond. The James Webb Space Telescope puts peer deeper into the cosmos than ever before, may reveal the atmospheres of distant exoplanets, perhaps even signs of life. It'll show us new parts of space history, things we cannot yet imagine, questions we have not yet asked. Space history is not a distant memory, but a living, breathed story, one we are writing with each new discovery, with every question we dare to ask. As I look out from this window, I see not just the stars, but the echoes of the past, the whisper of future journeys, and the certainty we are only at the beginning of our exploration. The universe is vast, its mystery boundless, and we, like our ancestors who first gazed up at the sky, are only just beginning to understand our place within it. The stars shine beyond, vast and endless. Yet within that boundless expanse lies the record of our first humble steps toward the infinite. Each of those steps, Sputnik, Gagarin, Apollo, carries with it the pulse of human curiosity, the relentless drive to understand not just where we are, but where we might one day go. That same drive, pushing us to peer deeper into the cosmos, now brings us to the precipice of new discoveries, as we turn our gaze not just to the stars, but to the worlds orbiting them. Through this window, I think about the worlds we've yet to see with our own eyes, the exoplanets hidden in the light of distant stars, planets we've only begun to detect, watching our stars dim ever so slightly as they pass in front of them. These are new frontiers of space history, planets that may hold oceans, clouds, and atmospheres filled with chemical signatures of life. Take the TRAPPIST-1 system, with its 7 rocky planets circling a cool dim star. From our vantage point, TRAPPIST, one is just a flicker of light in the constellation Aquarius. But through the lens of our instruments, it becomes a vibrant system full of potential, with planets locked in a delicate gravitational dance. What would you like to stay on one of those worlds, looking up at the sky and seeing 6 other planets, large as moons, hanging overhead? This is the new space history unfolding. Unlike the moon or Mars, places we dreamt of walking on, these exoplanets are so distant that even with our fast spacecraft, we remain unreached for now. But through telescopes like Kepler, TESS, and the upcoming James Webb Space Telescope, we are beginning to unravel their mysteries. We can detect their atmospheres, search for water vapor or methane, and speculate whether they're bathed in sunlight or trapped in our night. I look out from this window, I see not just the future, but the delicate atoms that connect all of this. How magnetic fields shape stellar winds, how starlight breaks through exoplanetary atmospheres, how the chemistry of the distant world may tell if life has taken hold there. These are just eyeglass. They're the questions that define the next chapter of space history. And yet, there's always the awareness that we are in early pages of this history. The space telescopes we've launched are at the beginning. They've shown us the possibility there are thousands, maybe millions of planets like Earth, orbiting stars at just the right distance for life to flourish. These planets hold the key to answering the oldest questions humanity has ever asked. Are we alone? It's incredible to think that the light from those distant worlds, as it passes through their atmospheres, is bringing us answers slowly, quietly, but surely. The same light, the spectra we observe, carries the thing that's life, like written in the absorption line of gases like oxygen, water, and carbon dioxide. But beyond the science, beyond data, there's something deeply human about this view. We've always looked outward to the stars for inspiration and wonder. Now, through the lens of our telescopes and the windows of our spacecraft, we are seeing more than just the faraway stars, planets. We're seeing a seed of our future. Maybe one day, not too far from now, we'll send missions to some of the exoplanets. Perhaps find one with oceans and breathable air, a place that feels strangely familiar in its distance. Maybe we'll look back in this time, from a future spacecraft window, orbiting these distant worlds, and think how far we've come. We'll remember the nights spent gazing at the stars, wonder it was life out there, and we'll realize we're already part of something larger, something cosmic. From this window, we are part of space history, and it's still being written. Every discovery, every new exoplanet we identify, brings us closer to the possibility of not alone in this universe. The future of space history is unfolding, just beyond our reach. The atmospheres of distant worlds and starlight that have traveled millions of years to meet our eyes. Space history is not just about the past or the future. It's about now, the moment we're in, where our imaginations meet the reality of the cosmos. But more than that, beyond history that we've written so far, we've glimpsed the worlds that beckon us forward. Beautiful worlds, strange and wondrous, each with its own story, waiting to be discovered. Through the window, we imagine planets bathed in the light of red suns, sky painted in hues we've never seen on Earth. Worlds like Proxima Centauri b, bringing the closest star to our own, tantalizingly within reach. That's a place where oceans lap against alien shores under a dim, crimson sky. Proxima Centauri b, our nearest exoplanetary neighbor. Proxima Centauri b, the closest known exoplanet to Earth, or the star Proxima Centauri, a red dwarf located 4.24 light years away in the Alpha Centauri star system. Discovered in 2016 by the European Centre Observatory (ESO) using the radial velocity MED, Proxima Centauri b quickly became one of the most exciting exoplanets ever found. Not only close in astronomical terms, practically in our cosmic backyard, but it also lies in a habitable zone of the star, meaning conditions can allow for liquid water on its surface. This discovery makes Proxima Centauri the A prime candidate in search for habitable worlds beyond Earth. Proxima Centauri b was discovered by measuring the slight wobbles in movement of its parent star. The planet has a minimum mass of about 1.17 times that of Earth, classified as an Earth-like planet or super-Earth. Its orbital period is about 11.2 days, meaning it completes a full orbit of a star much faster than Earth does around the Sun. Despite the close orbit, Proxima Centauri lies within the habitable zone, the region around a star which could allow for liquid water, a key ingredient for life. Because Proxima Centauri is much cooler and dimmer than the Sun, habitable zone is located close to the star. Proxima Centauri orbits at a distance of about 5 cents astronomical units, only 5% of the distance between Earth and Sun. While this might sound perilously close, the reduced luminosity of Proxima Centauri means the planet receives roughly the same amount of starlight as Earth does from the Sun. Tidal locked world. The most intriguing, yet potentially challenging aspect of Proxima Centauri b is the likelihood that it is tidally locked. This means the side of the planet constantly faces its star, while the other side reigns in perpetual darkness, much like the Moon's relationship with Earth. If Proxima Centauri b is indeed tidally locked, it would have extreme temperature variation between its day side and night side, with one hemisphere receiving continuous sunlight and the other shrouded in eternal darkness. The day side could be blisteringly hot, with direct exposure to Proxima Centauri radiation, while the night side might be freezing cold. However, in terminator zone, the region between day and night sides, temperatures might be more moderate, potentially creating habitable conditions. In this twilight region, liquid water might exist, and life, if present, could potentially thrive in this narrow band where conditions are more stable. If Proxima Centauri has a thick atmosphere, it could help redistribute heat from the daylight to the night side, reducing temperature extremes. In this scenario, atmospheric circulation would play a crucial role in shaping the planet's climate, allowing for more uniform temperatures across the surface. Oceans, if they exist, could also help moderate the climate heat, making the planet more hospitable for life. The possibility of an atmosphere. Whether or not Proxima Centauri has an atmosphere is one of the questions regarding its potential habitability. A thick atmosphere would not only help moderate the planet's climate, but it could also protect the surface from harmful stellar radiation. However, the stellar flares from Proxima Centauri could have significant consequences of the planet's atmosphere, potentially stripping away over time. Stellar flares emit high-energy particle and radiation that erode the planet's atmosphere, particularly planets orbiting close to their star, like Proxima Centauri b. Without a strong magnetic field or protected atmosphere, Proxima Centauri b is exposed to radiation, making it difficult for life to survive on the surface. Despite these challenges, some models suggest that Proxima Centauri b might have a dense atmosphere, possibly due to a strong magnetic field or other protective factors. If the planet does have an atmosphere, it would be key to understanding its potential habitability. Future missions and telescopes, such as the James Webb Space Telescope, may be able to study the atmospheric composition of Proxima Centauri b, provide critical data about its environment. Proxima Centauri's flares and their impact. One of the major hurdles to life on Proxima Centauri b is the intense stellar activity of its parent star. Proxima Centauri, like many red dwarfs, regularly emits stellar flares, bursts of radiation that dramatically increase the amount of ultraviolet and X-ray radiation hitting the planet. These flares can strip away the atmosphere and damage any potential biosphere. The 2017 elevation captured one of the largest flares ever seen from Proxima Centauri, which temporarily increased the star's brightness by a factor of 1,000. Such flares, if frequent, could be devastating for a planet like Proxima Centauri b. However, some scientists believe that if the planet has a sufficiently thick atmosphere or a strong magnetic field, it could still retain habitability in certain regions. One possibility is that life on Proxima Centauri b, if it exists, could adapt to these flares. Life forms might evolve to thrive underground or beneath oceans, where they would be from the most harmful radiation. Alternatively, life could exist in a shadowed side planet, protected from the intense radiation of a flaring star. Potential habitability and search for life. Despite the challenges posed by proximity to a flare star and potential tidal locking, Proxima Centauri b remains one of the most promising candidates for habitability outside of our solar system. If liquid water exists on the surface and the planet has a dense atmosphere, Proxima Centauri b could harbor life, possibly environments similar to the deep ocean ecosystems on Earth. The potential for life in the twilight zone, where temperatures are more stable, is one of the most exciting aspects of the planet's discovery. In such a scenario, the interplay between light and dark could create complex ecosystems that are shaped by the unique environment of a tidal locked world. Even if life does not exist on the surface, it is possible that microbial life could survive in surface environments, protected from the harsh conditions above. In the coming years, astronomers hope to study Proxima Centauri b in greater detail. Instruments like the James Webb Space Telescope and ground-based observatories allow scientists to analyze the light from Proxima Centauri b as it passes through the planet's atmosphere, searching signs of water vapor, oxygen, and other gases that indicate habitability. Breakthrough Starshot, an ambitious project by physicist Stephen Hawking and billionaire Yuri Miller, aims to send small, powered spacecraft to the Alpha Centauri system within the next few decades. The probe, successful, could provide direct imaging and data on Proxima Centauri b, offering unprecedented glimpse into this nearby world. A vision of Proxima Centauri b. What might Proxima Centauri b look like? Imagine standing in the twilight zone, with one side of the sky glowing with the faint light of a red dwarf star, while the other side fades into deep, endless night. The atmosphere, if present, might be the clouds and strong winds sweep across the surface as heat from day side is carried to the night side. In the distance, towers form day side, where the constant heat drives powerful patterns. Oceans, if they exist, might turn into a pull of the planet's tidal forces, with waves crashing on dark, rocky shores in the twilight. On the night side, the temperature could drop dramatically, freezing oceans and creating vast expanses of ice. Beneath the surface, in the depth of the ocean, or within the planet's crust, life could thrive. It could survive in extreme conditions, shielded from radiation above. Microbial life, similar to the extreme that survive in Earth's harshest environments, could be the dominant form of life here, playing in narrow regions where conditions are just right for survival. The future of exploration. Proxima Centauri b is not a curiosity, it's a target. Its proximity to Earth means that's one of the few exoplanets we can be able to study in detail within our lifetimes. Future missions to the Alpha Centauri system, combined with next-generation telescopes, may allow us to determine once and for all whether this planet habitable or even inhabited. Could we one day walk there, feel the faint warmth of a distant star on our skin, and look up to the unfamiliar constellations? Then there is Kepler 452b, a world that has been called Earth's cousin. Orbiting in the habitable zone of a star much like our sun, Kepler 452b might be green green. Its landscape lush and fertile, thick clouds drifting lazily above a landscape of towering mountains and deep valleys. There perhaps rain falls just as it does here. Nourishing life grows and evolves untouched by human hand, but connected to us by the same cosmic force that shape our own Earth. And the worlds that circle distant stars like LHS 1140, a rock just 40 light years away. The gravity might be stronger, the heavier, but with an atmosphere rich in possibilities. Perhaps dense clouds swirling across a cobalt blue horizon, with winds carrying the scent of alien oceans. Thin life we have yet. Blood air may be faint. A soft glow of a red dwarf star, casting the landscape in perpetual twilight. Oh, forever on the cusp of dawn or dusk. In Trappist, one system, 7 rocky worlds orbit cool, M's are. Each unique and beautiful in its right. And just ending on one of those planets, with the other 6 hanging low in the sky, like moons. The sun sets there might be like nothing we've ever seen. Deep purple skies fading in amber, with bands of starlight filtering through the thin atmosphere. What life could thrive in such a place, under the gentle glow of an ultra-cool star, where days stretch long and the warmth is ever so faint. Beyond the stars we know, there are surely worlds to fight all estimates. Planets where seas of methane glisten on emerald skies, or where clouds of ammonia rise high above mountain ice. There could be gas giants with moons as beautiful and varied as the planets themselves, some covered in tropical storms that rage for centuries, others with crystal clear oceans that reflect the stars as though they were mirrors. And there might be water worlds, entire planets covered in oceans, with endless waves stretching from horizon to horizon, formed by a distant sun and teeming with life in its depths. One can only dream of the beauty of a world like LEED 581G, an exoplanet that orbits a star in the habitable zone, where the temperature is like liquid water. Perhaps this world is cloaked in mist and surface obscured from our distant gaze, a place where life flourishes in the watchful eye of a red sun. Trees with leaves dark at night might stretch toward the sky, gather every last photon of light, while rivers of crystal clear water carve paths through fertile plains, home to creatures as varied and wondrous as the ecosystem of Earth. LEED 581G, potentially habitable exoplanet. LEED 581G is one of the most intriguing exoplanets ever discovered, orbiting stars 20 light years away from Earth. Founded in 2010 by astronomers using the Keck Observatory in Hawaii, Gliese 581G quickly captured the imagination of scientists and space enthusiasts alike, because it lies in what known as the habitable zone, the region around a star where conditions may be just right with water to exist. This discovery led speculation about whether Gliese 581G could support life, making a focal point in search for like exoplanets. The star, Gliese 581. Gliese 581 is a star called Gliese 581, a red dwarf located in the constellation Libra. Red dwarfs are smaller, cooler, and much bigger than a sun, but they're most type of star universe. Despite being much less luminous, red dwarfs often have long, stable lifespans, meaning planets orbiting them could enjoy relatively stable conditions for billions of years, an important factor in the potential for life to develop. Gliese 581, like many red dwarfs, is a star that exhibits stellar flares, some bursts of energy that can release powerful radiation. This type of activity could be a challenge for habitability, particularly for planets close to the star. However, because Gliese 581G lies right in the middle of the habitable zone, there's hope that its atmosphere could exist to protect the planet from radiation, create a stable environment on the surface. The discovery of Gliese 581G was made by analyzing the radial velocity of the star, essentially how the star wobbles due to the gravitational pull orbiting planets. This technique allowed astronomers to detect multiple planets in Gliese 581 system, including Gliese 581G, which is how orbit in the star's habitable zone. The planet itself is estimated to be super-Earth, meaning it is larger than Earth, but smaller than gas giant Neptune. Gliese 581G was initially thought to be about 3 to 4 times the mass of Earth, with a radius about 1.5 times larger than our planet. Its year, one complete orbit around the star, takes just 13 days, meaning it is much closer to Gliese 581 than Earth is to the Sun. However, because Gliese 581 is dim and dwarf, this proximity places Gliese 581G right in a sweet spot of the habitable zone, where temperatures allow for liquid water to exist at the surface. Could Gliese 581G support life? One of the most exciting aspects of Gliese 581G is its potential to harbor liquid water, which is considered essential for life as we know it. If Gliese 581G has an atmosphere, it could add an insulating layer, helping regulate planet temperature and possibly allowing for oceans or lakes of liquid water. However, there's an important caveat. Tidal eye, like many planets orbiting red dwarfs, Gliese 581G is like tidally locked, meaning one side of the planet is always facing the star, while the other side is in perpetual darkness. This would result in extreme temperature difference between the day side and the night side. The side facing the star might be extremely hot, while the dark side could be freezing cold. But between these two extremes, there could be a twilight zone, a region where temperatures are moderate enough to allow for liquid water and potentially life. In this twilight zone, temperatures could be mild, and if there is water, it might flow in the form of rivers or pool into lakes or seas along the boundary between light and dark. Presence of atmosphere would be key here. A thick enough atmosphere could help distribute heat around the planet, creating more temperature across larger regions, rather than just at the boundary. The possibility of an atmosphere. Today, we don't know what Gliese 581G is an atmosphere, and that remains one of the planet's greatest mysteries. If it has a substantial atmosphere, it could protect the surface of stellar flares emitted by Gliese 581 and help regulate planet temperature. The atmosphere also provide clues to the possibility of life. If we were able to observe the planet's atmosphere in detail, we would look for specific factors such as water vapor, oxygen, methane, carbon dioxide. These gases are associated with the process of life on Earth, and the presence of Gliese 581G could be a promising sign of biological activity. However, even without these specific markers, an atmosphere that provides the right conditions for liquid water would be an exciting discovery. In the absence of an atmosphere, Gliese 581G would likely be a barren, inhospitable world. With atmospheric pressure, heat water in liquid form. Any water would either freeze solid on our side, evaporate in space side by side, making the planet unlikely to support life as we know it. The controversy. Despite the initial excitement, the existence of Gliese 581G was later called into question by such astronomers. In 2014, new data suggested that what appeared to be a signal for Gliese 581G might actually be caused by stellar activity, specifically magnetic activity on the surface of the star. This stirred debate within the scientific community, with some researchers arguing that Gliese 581G discovered could have been a false positive. However, controversy did not fully close the case on Gliese 581G. Some astronomers still believe the planet exists, but that more detailed observations are needed to confirm its presence. The Gliese 581 system remains a prime target for further study as other planets in the system, including Gliese 581D, also lying near the habitable zone, making it one of the most promising nearby star systems in search for habitable worlds. The future of Gliese 581G exploration. While Gliese 581G's status remains uncertain, it highlights the conscious excitement of discovering potentially habitable exoplanets. Future telescopes, such as the James Webb Space Telescope, are expected to bring us much closer to understand distant worlds like Gliese 581G. These instruments will be able to analyze the light passing through exoplanet atmospheres, providing detailed information about composition and driver. In the case of Gliese 581G, one of the most important steps will be to confirm its existence and then focus on determining whether it has an atmosphere. If we find that it does, the next step would be search for signs of habitability, such as the presence of water vapor or other biosignatures. Even if Gliese 581G proves not to exist, the search for Earth-like exoplanets in the habitable zone of nearby stars continue. Red dwarfs like Gliese 581 are prime targets because their small size and cooler temperatures make it easier to detect planets orbiting close by. The discovery of Gliese 581G has always shifted the focus of exoplanet research toward these small, dim stars, with the potential for habitable worlds mighty greater than we ever imagined. A vision of Gliese 581G. If Gliese 581G exists, what might it look like? Imagine standing on the surface of a tidally locked planet, with one side forever bathed in light and the other shrouded in eternal darkness. In the twilight zone, the sky glows with a pale orange or red hue, reflecting the soft, dim light of a red dwarf star. The landscape might be rocky and barren in place, but along the edge of the light, liquid water could flow in rivers and collect in seas. The air could be dense with moisture, swirling hazards that balance the extreme temperatures between two sides of the planet. As you look right around, you might see some cloud gathering, where heat from the stars rise in intense distance. Behind you, the sky fades in deep darkness. The stars glimmer coldly over a frozen landscape. Life that exists might cling to borderlands, where the balance of light, water, and temperature creates just the right conditions for survival. In search for life beyond Earth, Gliese 581G remains one of the most fascinating and enigmatic possibilities. Whether it proves to be a real planet or just a false signal, its discovery has opened our eyes to the potential of the universe, showing that the ingredients for life could be scattered across the cosmos, waiting for us to find them. And what about mysterious water-rich planets that might exist in abundance? Imagine a planet where astronauts float on vast, deep oceans. Their surface is of glowing bioluminescent life. Beneath the waves, ancient creatures swim through the depths. Their movement is slow and graceful, as the oceans themselves breathe in time with the tides of a distant star. The skies above the water world might shimmer with auroras, caused by magnetic fields far more powerful than anything we know on Earth, create dazzling displays of light as particles from the parent stars interact with the planet's atmospheres. Perhaps the most beautiful worlds are those that challenge our understanding of what light can be. Planets that orbit binary stars, where two suns pass overlapping shadows, creating twilight zones where life might flourish in the delicate balance of light and dark. The landscapes of the world can be otherworldly, sand dunes stretching out on two suns, with deep canyons carved in the wind that howl through them. Or Perhaps the surface is dotted with glassy like reflectable stars. Their surfaces rolling in the wind like pools of liquid light. As we look out from this window, we are filled with a sense of awe and possibility. The universe is not a cold, empty place, but a canvas filled with vibrant worlds, each one with its own unique beauty and its own story to tell. The light from these distant planets has traveled for thousands, millions, even billions of years to reach us. And as we study that light, we begin to understand that the beauty of the universe is far more complex and diverse than we ever imagined. Even worlds, seen or unseen, represents a new chapter in the story of space exploration, a chapter that humanity has only just begun to write. We have taken our explorers to the edge of our solar system, but the real journey is just beginning. With each new telescope, each new mission, we are opening windows into new worlds, reveal the wonder of the universe one planet at a time. These beautiful worlds, with their alien skies, unfamiliar landscapes, and untold secrets, are waiting for us. They are out there, just beyond our reach, but closer than ever before. Through the light we capture, through the missions we send, and through the dream we pursue, we're getting close to understanding not just the universe, but our place within it. One day, perhaps, we'll stand on one of those beautiful worlds, looking up in a new sky, knowing that from a window long ago, we first caught a glimpse of vastness and beauty that awaited us. In the tapestry of the cosmos, there are few as captivating and mysterious as binary stars, pairs of stars bound together by gravity, orbiting a common center of mass. These celestial duos are not rare. In fact, nearly half of all stars in the universe are part of a binary or multiple star system. But it's their dynamic, complex relationships that make them so fascinating. As we peer through the window of space exploration, we catch glimpses of these systems and planets that might orbit within them, revealing a universe far more intricate than once imagined. A cosmic dance of light and gravity. At first glance, binary stars may appear similar to solitary stars we're familiar with, like our own Sunday. But these pairs of stars are locked in a delicate dance, their gravitational pulls keeping them in constant motion around one another. This movement creates a high, where stars orbit a common center of mass, sometimes so close they nearly touch, at other times separate with vast distances. Some binary star systems are composed of stars of similar size and brightness, while others are more extreme, with one star much larger or more massive than its partner. These contrasting pairs, like a supergiant and dwarf boundaries, create extraordinary contrasts in their interactions. Massive, radiant stars pulling on smaller companions with such force that their outer layers are sometimes stripped away, feeding the larger stars insatiable energy. Binary stars vary in their proximity and relationship to each other. Close binaries orbit in such high proximity that they exchange material, often resulting in dramatic stellar phenomena like movie, or even the eventual merger of the two stars into a single, more massive one. In contrast, white binaries may orbit at distances so great they take thousands of years to complete a single revolution, appear more like two independent stars from an observer's perspective. These wide systems can have planets orbiting one or both stars in intricate orbital resonances, creating a complex and dynamic environment for any planetary system. Two suns in the sky, the worlds of binary stars. One of the most mesmerizing ideas about binary stars is to imagine what it would be like to live on a planet orbiting such a system. Picture a sky with two suns, each casting its own unique light across the landscape. In some binary systems, one sun may be larger and broader, dominating it, while the other is smaller, offering a softer, secondary light that waxes and wanes as the stars move through orbital paths. The skies of such a world would shift dramatically, with the dense of suns creating days and nights at varying brightness and length. Some planets orbit stars in what is called the Cuminary orbit, where the planet circles around the entire binary pair, much like the planet Tatooine from Star Wars, which famously had two suns in its sky. These Cuminary planets must navigate the gravitational tug of war between the two stars, creating high stable orbits in some cases and chaotic, unpredictable paths in others. For a planet in such a system, the rhythm of the star's motion could cause dramatic shifts in temperature and light, leading to scenes more extreme than anything we experience on Earth. In other binary systems, planets orbit just one of the stars while the second star orbits at greater distance. These planets experience weird changes in the sky as the second star comes into view and then fades away, particularly leading to periods of double sunrise or sunsets. Imagine standing on a planet like this, watching one sunset in the west, while the other hovers low on the horizon, its light casting soft, low, long into evening. Kepler 16b, a circumlunar planet discovered by Hubble's telescope, is a real-world example of this. It orbits a pair of stars in the constellation Cygnus, and skies would be a stunning display of celestial choreography, with two suns rising and setting sing with planets orbit. The discovery of Kepler 16b was a watershed moment, proving that planets can indeed exist in stable orbits around binary star systems, and opening up new possibilities for where we might find habitable worlds. The science behind binary stars, interaction, and evolution. The relationship between two stars in a binary system can be peaceful as it is violent. In close binary systems, where the stars are near enough to influence each other's evolution, a process known as mass transfer can occur. When one of the stars in a close binary begins to swell into a red giant end of its life, the outer layers can spill over onto its companion. This can result in one star growing significantly in mass, while the other shrinks, or even loses outer limb entirely, becoming a white dwarf or non-compact star remnant. The most extreme version of this process occurs in contact binaries, where two stars are so close that they share a common outer envelope of gas. These systems are often unstable and eventually merge into a single star, where they can result in dramatic stellar explosions as a nova. Material from one star falls onto a white dwarf, leading to a thermonuclear explosion that briefly outshines the entire galaxy. In some cases, binary stars can end their lives in spectacular fashion. Both stars in the system are massive enough. They may both go supernova, leaving behind two neutron stars or black holes orbiting another. Stellar remnants can continue their dance, spiraling closer and closer together as they lose energy in the form of gravitational waves. Ripples in space-time predicted by Einstein's theory of general relativity and detected for the first time by the LIGO Observatory in 2015. When two neutron stars or black holes finally collide, they release a burst of energy so powerful that it can be detected across the universe. Habitability on binary stars. Life in a dynamic sky. One of the most exciting questions surrounding binary stars is whether life could arise on planets orbiting these systems. The complex gravitational interactions between two stars create unique environments, but they do not necessarily exclude possibility of life. In fact, binary systems may offer some advantages. For planets in circumlunar orbits, the combined gravitational pull of the two stars can create highly stable orbital regions, known as habitable zones, conditions that might allow liquid water to exist on the surface. In such systems, the changing light from two suns leads to fascinating variations in climate and weather, potentially giving rise to life forms adapted to fluctuating conditions. Planets orbit just one of the stars in a binary system might also experience periods of enhanced energy as the second star approaches, potentially boosting photosynthesis and other biological processes. Life on cycles could evolve to take advantage of these cycles, thriving during the times when both star light reaches the planet's surface, and entering periods of buoyancy reduce activity when one star recedes. However, binary star systems also present challenges. The complex gravitational dynamics can make planetary orbits less stable, and the intense radiation from certain types of stars, such as red giants or massive blue stars, pose significant Earth. But the discovery of planets like Kepler 47c, a gas giant orbiting a binary star, suggests that planet formation is possible in these systems. And where there are planets, the potential for life remains. Next, right here, explore binary systems. As we peer deeper into the universe, the study of binaries are continuing to play a crucial role in our understanding of stellar evolution and the search for habitable worlds. With the advent of advanced telescopes like the James Webb Space Telescope, we are poised to explore these systems in even greater detail. JWST will allow us to observe the atmospheres of exoplanets or binary stars, helping us determine whether these distant worlds support life. Future missions could also send probes to the Alpha Centauri system, the closest binary star system to Earth, located just over 4 light years away. Alpha Centauri consists of two stars, Alpha Centauri A and